I was just trying to think of anything to put in that right before I went live. They work Saturdays, usually 2 a month. Oh, that's still annoying though. All right, Thunder, I see you DM'd me a question. You're really good at asking questions that I like just barely know how to do if I struggle enough. You're saying for part B, you need to know a better method. Okay. Linear algebra, my arch enemy. Eigenvector without the eigenvector? Oh god. We're not allowed to do eigenvectors when it literally like means invariant point. Okay. I mean, that's the same as the Millennium Prize people will pay, right? I guess it doesn't make a difference to me where the $1 million comes from. I don't think you'd be making any money though. Isn't it just $1 million? So PQ or linear transformations makes sure information M is formed by first applying Q, P, then applying Q. So if you're first applying P, that means P goes on the right. I just want to make sure I know what M. Yeah, because B relies on M. So make sure that I'm getting M right. A right. Oh god, okay. Oh. That's clever, Viv. You're saying, okay, yeah, QP, that's what I was thinking. And then like the vector X or whatever would be on the right of that. Well, I guess it wouldn't make a difference if we do XPQ or QPX. I don't know. Well, they probably should make a difference, right? I don't know. It is QP though. I shouldn't overthink it. Okay. So show the invariant points of this linear transformation M form a line in the, or the invariant points form a line in the plane stating the equation of this line. So I bet this is like breaking out the definition of an eigenvector into a system of equations. That's what we're doing here. Oh. Okay, I actually do know how to explain this one. Thank you for just sending the answer keys. I don't know if I would have gotten to here on my own. I guess this works. So, Thunder, yeah, it's exactly what you're saying. It's eigenvector without doing the tricks we usually do for eigenvectors. The line doesn't have a plus C. Oh, yes, it's, there's never a plus C, I think, in linear algebra, because linear algebra always has vectors as starting from the origin. I don't think they think any harder than that. So you did for most of your proofs, look at the answers, and it's understood how to get the answer, but the final show you that's not the way. Exactly, Viv, yeah. The attempt for, like, even a failed attempt is really important. I need to show you another way. Okay. But yeah, I think for something like this, you should never get a plus B. I think. This person uses the method my teacher used, but you don't know how to apply it with the question I gave you. Okay. I've got a matrix and I'm not afraid to use it. Really? So here they consider a plus C. Oh, maybe you're writing it like that. Please do it with this method. We should never get a plus C, right? Because in linear algebra, you just always have vectors start from the origin arbitrarily. In physics, you certainly don't. Like in linear algebra, I thought you just always do have them. I guess this y component could have a plus C, but the overall vector starts from the origin. Yeah, I mean, I guess just for this setup, I guess it makes sense to have a plus C, but the overall vector is still going to start from the origin. Okay. Ugh. System rank theorem is your personal Sisyphus. Oh yeah, like the boulder you push up the hill and always just comes back down. You did do this in college that you know you've forgotten how. I don't think I've ever done it this way, but it doesn't look terrible to figure out. So why are they distinguishing between the two x's here? If we want invariant, why aren't we keeping these x's the same? Oh, invariant lines in general? Okay. I just learned them. I don't think I learned the term invariant lines. I just learned eigenvalues and eigenvectors. Hey Zappin. I'm scared by the word algebra 2 because that could mean like abstract algebra or linear algebra or something, but if you want, feel free to post a question there in chat or in Discord. Thanks for the follow yesterday, by the way. But if it's like high school level algebra 2, I can definitely do that. I'm working on a different question from Thunderfix, but you can be right after. Hey, Jed. Wait, oh, okay, that's not the end of the work. I was like, what does this mean? Count's now 36? Oh, nice. Ooh. Okay, let's just start setting things up and blindly flailing through this, because this is... Why would you do this? I don't get it. Like, we can do it, but like... Okay, so let's get our... We're gonna use this for M. Yeah, no, I believe you, Thunder. Sounds good, Zappin. Minus a half. Minus root 3 over 2. I really feel like that plus C is just weird. I feel like you shouldn't have to have it, but since you have to do it this way, that's like, I'll include it. I don't have to like it though, and I certainly won't. Okay. In high school, oh, cool. Sorry, because when I took a linear algebra class, I thought like, oh, it's like y equals mx plus b. It's gonna be super easy. And then I found out that linear algebra is something much harder. So whenever I hear just the word algebra, I'm kind of scarred from that experience. Okay, and so we have this equation. I don't know why these two x's aren't the same, but we can just buy it. Why are these M and C's the same? Okay, I really don't understand this setup, but I can follow it. Okay, so what we do is we plug in M, we plug in X and X. So M is -1/2 minus root 3 over 2 minus root 3 over 2 1/2. Little x is little x mx plus c. Big X mx plus c. And then we do this matrix multiplication. Just do that. That's 2 by 2, that's 2 by 1, so we're going to get 2 by 1. X times -1/2 is -1/2 x. Oh! Zach, thank you so much for the raid. Welcome in. I was lurking for a bit. Saw you were talking about some meta channel stuff, but I had a little bit of a busy morning, so I couldn't listen that close. I hope your stream was good, though. For anyone who's new around here, I'm Don. I do math help, much like Zach. And right now I'm going to try and struggle through a problem to find the invariant lines of this matrix using a very particular method. We can't just get the eigenvectors the normal way. We have to set up this equation for some reason, and then we're going to get a system of equations out of this. Hello, Zach. And hey, SG1 over on YouTube. All right. So now that we have this multiplication done, we can split them into two equations. Top row with the top row, the bottom row with the bottom row. So we get -1/2 x. Oops. Minus root 3 over 2 mx plus c equals big X. That's going to throw me off. Minus root 3 over 2x plus 1/2 mx plus c equals m big X plus c. And then we know that this thing is big X, so we plug it in down here. This is kind of painful. I'm going to multiply out the 1/2. I assume that's a good idea. I'm going to multiply in the root 3 over 2 as well. X minus root 3 over 2 c plus c. And then I think we're going to bring everything over to one side and set things equal to 0. Same so far. Oh, good. And I'm doing good at SG1. Thanks for asking. How are you doing? So we're going to group the x's with the x's, the constants with the constants. So let's put an x out here in parentheses and gather up all the coefficients of x. So we've got a minus root 3 over 2, a plus 1/2 m. That's minus 1/2 mx. We're going to add it to this side, so it's plus 1/2 m. That is minus root 3 over 2 m squared. But wait, that's minus, so it becomes plus. This is going to become plus. It's a constant, though. So let's close our parentheses. We've gotten all the x's. We have a plus 1/2 c there. Are all our constants going to have c? They are. So let's factor the c out. We have a plus 1/2 from there. We have, that's going to flip sign to be plus root 3 over 2 m. And then just the c becomes a minus 1 equals 0. I think we're good. So now let's combine like terms inside the parentheses and get something that isn't terrible, I hope. It kind of looks terrible though. Root 3 over 2 m squared plus m minus root 3 over 2. Three over 2m minus a half, 0. Okay. Got the same, good. And now we have to analyze this. So if we take x to be 0 first, like this website does, you don't know why to reject 1 over root 3? Me neither. I'm just going to blindly follow the website. So if I just let x be 0, then either c equals 0 or... So we're going to add 1/2 and then multiply by 2 over root 3, which becomes root 3 over 3. Because the 2's cancel, and you just get 1 over root 3. Okay. What do we do with that? Oh, you say 1 over root 3, but that's the same thing. And you're saying that's what we reject, apparently? Then equation star. I think what they're doing is they're plugging in this value for m over here and seeing what happens. So let's do that, because this we already know this part of the equation is going to be 0. So let's look just at this part equaling 0. Root 3 over 2, 1 over root 3 squared. We're going to get root 3 over 6. Plus root 3 over 3 minus root 3. Oh my god, dude. Okay, well that's going to be... This equals 0 on the inside. Because that's 2 root 3 over 6 plus root 3 over 6 is 3 root 3 over 6, which is positive root 3 over 2 minus root 3 over 2. I don't think we throw this out. Like, we get the opposite situation that the website has. Like, this statement is true for any x you want. Well, are we always supposed to get that solution gets thrown out? Why can't we just have a different situation? 1 over root 3 is wrong. I mean, this looks like 1 over root 3. Well, no, it doesn't. It looks like 3 over root 3. What is this? If m equals 1 over root 3, y equals x over root 3 doesn't work. So maybe there's some other reason that we can eliminate it. Because this is going to come up again in the second stage where they look at where they let c be 0. I think we need this maybe isn't necessarily an answer yet. Let's keep this root 3 over 3 in our back pocket because it's going to be helpful when we go to factor the quadratic. I think let's just proceed with the problem and see what else happens. Because if this one doesn't work, I assume we're going to get just one invariant line rather than two invariant lines. So either x equals 0, which it usually doesn't, or m has to equal 0 here. We already found 1, 0, which is root 3 over 3. I think I still want to do a quadratic formula, because I don't want to deal with doing polynomial division. So let's just do quadratic formula. Better safe than sorry. 1 minus... That'll be 3 over 4 times 4 is 3? That doesn't seem right. Oh wait, over root 3. That's why it's probably right. Minus 1 plus or minus 2 over root 3. So if it's negative 1, we get... Or sorry, if it's negative 1 plus 2, we get positive 1 over root 3, which is what we already got over here. Or if it's negative 1 minus 2, it's minus root 3 over 3, which is minus root 3. All right, so that gets us the answer that the answer key has. How do we know to throw out root 3 over 3, which is what your question is? I think so, just plug in 1 over root 3, but there has to be a better and faster way. Yeah. This is weird. It must be something from how we solve the system of equations. I don't see what that thing is, though. I mean, I guess the only thing I can think of that's significant is that 1 over root 3 is a solution for both of these equations to equal 0, whereas negative root 3 only works for this first one. If you plug it in over here, you just get something else. Like you get c equals 0 once you divide out the coefficient. Whereas if you plug in 1 over root 3, you just get 0 equals 0, which is a true statement. But maybe isn't meaningful? I don't know. Maybe... oh. Oh yeah, thanks, Jed. Yeah, Sep, and I haven't forgotten about you. It's just a tricky question. Dan says, after you wrote the system and set the two sides equal, can you double check that? I forget how you do this in Wolfram. We could check the... Oh, I mean, I guess we already know the answer should be. So, Thunder, I think in this setup you can have a plus C. I'm saying you generally... The final answer, I don't think should have a plus C. In this Y component, you can have a plus C, I guess. Even though it's weird. I feel like you shouldn't need one anyway. Even then, this is a weird way of solving system equations. Like, I don't really know what this means with letting x equal 0 and c equal 0. Maybe that's why I don't understand why we can throw out some of these solutions. Let me take a look at Zappin's questions, and if it is a quick one, we can take a little break here. Oh, the Directrix of a parabola. Yeah, it should be quick. I don't remember the formula for this, but it should be available online. Let me... Directrix of a parabola. This is, like, I was taught this once in Algebra 2, and I kind of never used it again. Oh, why do they give it to you in such an annoying form? Okay, they make you do some simplification here. We can deal with it, though. Oh, or maybe they're doing it because you need it in this form? Really? Is this some kind of messed up vertex form? I guess it is a different kind of vertex form. Hey, Flip Styles. K minus A? Thanks for the follow. So we can get it in this form, I guess. Latus rectum? Yeah, I remember that. I don't know how you don't giggle at the term latus rectum. So I guess, Zappin, before I get too deep into it, like, are you familiar with like having to get a parabola in this form? Because I want to make sure that, I feel like I was taught it some other way, and so I want to make sure I'm doing the way that you're taught. I'll keep this open, but like, I feel like there's just some more, hell no? Okay. So yeah, let me not do some crazy stuff that you're not supposed to do anyway. Do we just need it in, like, I can get it in vertex form, but like, I'm looking for what the formula is supposed to be. This doesn't look that familiar either, but like, hopefully that's legible on stream, but like, no, that's a parabola. Why is x squared? Oh, never mind. Why don't they just give me the formula, dude? I'm sorry. Directrixes are annoying. They do have some kind of meaning with parabolas, but like, You're just annoying. The same as the focus? It's related to the focus. I remember that much. What an annoying form to get it into, Thunder. I see what you sent me. Actually, I guess that's not that annoying. It's just vertex formatted different. Yeah. So, I mean, how do you get the focus of a parabola? I don't know that either. I don't remember that either, anyway. I've done it. Oh, that's the same weird thing. I mean, Zappin said they haven't had to get into that form before. Okay, this seems more understandable. If you get it into vertex form, this is your focus. Okay, we can just apply this formula. Geez. And then once we know the focus, we can work out what the directrix is. Okay. So, Zappin, I guess I hope you're comfortable with getting things into vertex form. Oh yeah, let me show it again. Like, do you just know how to get a parabola into vertex form and then do this? Yeah, easy. All right. I'm taking that as a go-ahead for the question. I wonder if you could... Actually, it is multiple choice. There's probably some way to game this. But let's do it the intended way. Let's erase just the red work and do it on the left side. The red work isn't all that valuable. All right. So we have 6y minus 2x squared. All right, so they gave it to you in about the most annoying form they possibly could. Oh, yeah, thanks, Jed. I'll take that away then so I get a bit more room. All right, first off, let's isolate y and then get into vertex form. So I'm going to start by adding the 2x squared and the 8x to the other side to get 6y equals 2x squared plus 8x minus 4. Then I'll divide out the 6, that way we get y to be alone here. 2 divided by 6 is 1/3. 8 divided by 6 is 4/3. 4 divided by 6 is 2/3. All right, so we get some fractions. That's annoying, but we can deal with it. And I always get mixed up with completing the square when there's a leading coefficient. So at this point we can try to complete the square, but I'm gonna do a little extra step here and factor the 1/3 out of these first two terms. The minus 2/3 we don't care about for completing the square, that can just stay outside. But now inside here, we can complete the square. And I like doing this, taking the 1/3 out, just because having the equation on the x squared, it makes things weird and I make mistakes with it. So this way, I just know it always works. So if you want to complete the square on x squared plus 4, you do b over 2a. So 4 over 2 times 1 is just 2. Actually, that's what's going to factor to b over 2a squared. So we want a plus 4 and a minus 4, because we add b over 2a squared, like we do the plus and the minus of that. That's the trick for completing the square. And what you'll get once you actually factor it is just b over 2a, not squared. So it's given in both like forms. That's right. Or is it the 2a part, Jed? Check that last fraction. Oh, okay, you're right. I thought commenting the b over 2a squared. I did flip that 2/3. Thank you. All right, so now just this chunk here factors to x plus 2 squared. The minus 4 is still hanging out on the outside. And now this is the part where I have to undo the trick that I went with taking the 1/3 outside. So I'm going to distribute the 1/3 to the x plus 2 squared and distribute the 1/3 to the minus 4. It's a little bit weird to do it this way, but I find I make way fewer mistakes completing the square like this. So that's how I always do it. Now let's do this fraction math. So -4, they already have a common denominator, so we do -4 minus 2 is -6. -6 over 3 is -2. So that's our vertex form. B over 2 squared. Yeah, I engineered it so that a is 1 anyway. I think in general, you need the a if you're going to be brave and include that 1/3 there. But I always mess something up, so I take the 1/3 out front to force a to be 1. I think technically the general formula is that, but I never do that. So if you do it the way that I did, it's just always b over 2 squared. And so now we need that formula we were just looking at. So the focus, well, I guess we can list a few things about this parabola. The vertex is -2, -2, right? Because that one you flip the sign, and that one you don't flip the sign. The focus, the x-coordinate stays the same. The y-coordinate is our formula. K plus 1 over 4a. K is the y-coordinate plus 1 over 4, then a is 1/3. So we get a fraction and a fraction. That's okay. We just have multiplication here, and 1 over 3, we can unflip it, and the 3 can come all the way up top. So 1 over 4 times 1/3 is the same as 3 over 4. And now that's fraction math that's probably a bit more familiar. Get a common denominator. It'll be -8 over 4 plus 3 over 4 is -5 over 4. There we go. So that's our focus. Is that right? Yes. Okay. So I'm going to draw a little picture here. I think we could just use the numbers here to work it out, but I just want to see what's happening personally. So I'm going to just draw kind of a rough picture. Our vertex is at 2, -2, right there. Our leading coefficient is positive, so the parabola opens up vaguely. This part I'm not going to be exact about. Our focus is at -2, -5/4 is 1, -1 1/4, so just past -1. That means the directrix is going to be, if this is -1 1/4, that's -2. That's a difference of 3/4. So we're going to do two. We're going to go 3/4 down from the vertex to be 2 3/4. That's a mixed number, which I kind of hate. So I'm going to make it an improper fraction. 4 times 2 is 8, plus 3 is 11. So I'd say that's our directrix is y equals, how did we do this? We did -2 minus, and then the distance between the vertex and the focus. Oh, good. That's one of the options. I didn't even check that yet. The distance between the vertex and the focus in the y coordinate. Yeah. I just want to show it numerically too, Jed. Or when actually, like, if you didn't want to graph it, I just want to show that you can do it without like graphing it. I didn't say directrix equals, I should say directrix colon. I want to make sure I set this up right, because I want to make sure the sign is okay. -5/4 minus -2. It's -2 minus 3/4. And that gets you the same answer. Okay. So yeah. Zappin, let me know if that makes sense. I kind of glazed over the fraction math a little bit, but I have to back up and explain it more. What to use Directrix for? As far as I've learned, not much. A parabola is a conic section, of which I think there's 4 total conic sections: parabolas, circles, ellipses, and hyperbolas. They all have foci and directrixes, at least one of each. And those guide how you graph it. And I assume it has some type of significance for physics. Like, I think the orbits of planets are ellipses, and the planet is one focus of the ellipse, and the other focus, I think, is a significant part of orbital mechanics, which I don't know the specifics of, but I think there are technical applications for it. I haven't run into them yet, though. So as far as I've learned, they're mostly useless, but I think there are applications if you dig deep enough. Thank you. All right. No problems, Zappin. Thanks for the question. All right. Oh, it's hide problem. So I'm not sure if Wolfram is going to be much help with Thunder's question here. Thank you for doing that, Jed. Yeah, no worries, Jed. I want to evolve that anyway. Like I want to improve it so I can get timestamps for when we do things, so it'll help me go back through the YouTube VODs and get timestamps for when I'm working on what problems and make an actual queue as well. They put a queue into Enigma bot, but I want to hopefully make one that's a bit more suited to my needs. Vector projection. No clue? Oh gosh, okay. Well, before we get into that, do you want to like try to get to the bottom of this linear transformation question? Which I'm still not sure of how we're going to do that, but before we open up a different can of worms, let's try to finish our first one. The vector projection matters less. Okay. So we have an equation that's like this. So that first time that we got 1 over root 3 was when x equals 0, which isn't usually true. So what was the purpose of doing this? Yeah, I think we have a different situation here. And I'm trying to follow with their logic and apply it to this problem, but like... Ooh. Oh, no. Hey, Martin. How's it going? Nothing much with me. Oh, really? I've never heard of Math Panda. And hey, Alejandro. Explain why in some cases working with double integrals and limits contains functions it's necessary to change the order. You technically don't have to change the order, but realistically you usually do, because it's possible with double integrals to do things in like the wrong order, and you get something that's not easily possible to integrate. Maybe not even possible to integrate at all, actually. And it's kind of like a trial and error thing where you try one order. If it doesn't work, you try switching up the order. But it's just possible that you get some really weird, extremely difficult or impossible integrals with multiple integrals. You're in 10th grade math. Can you explain me a problem I'm not being able to solve? I mean, I could tell you mechanically what to do for a problem, but I don't think that's really going to help you. Explaining a concept might be more helpful, but that would take a lot of time. I'm not exactly sure like what type of concept you would be helpful. How is it possible to have an invariant line not passing through the origin? That makes no sense to me. Oh, I thought you were asking in general, Martin. If you have an actual problem that you want to see, feel free to type it out there in chat or put it in my Discord. Whatever's easier. Sorry if I misunderstood you there. Invariant line experts. It seems like a similar idea. Sounds good, Martin. I don't think Jed knows linear algebra. I don't really know linear algebra either, I feel like, to be honest. This is just a weird calculation to have you do, though. Like, this is so much more painful compared to just getting the eigenvector. No, it doesn't use the cross product at all. It's just getting determinants in a couple of different cases. Can you explain the way to organize the integral when necessary? That's a very well. Hey, good luck on your final tomorrow, Alejandro. That's a difficult question to answer. Aside from just practice a lot of them, and you'll see the pattern eventually. Which is unfortunate when your exam is tomorrow. A lot of times, if you have like a trick that I can show you is just like being comfortable with the change of variables. Like if you see an x squared plus y squared or something that looks like a circle, you probably want polar coordinates, for example. Why don't they show, like, if you have anything that looks like an x squared plus a y squared or some like rearrangement of this, a lot of times it's polar coordinates, for example. But yeah, I know it's kind of hard to say it in general because you can really just, there's multiple different valid ways to set up an integral, but they're not always possible or easy to integrate. And you can't really figure it out until you try to integrate it, unfortunately. Yeah, Jed, for done a problem about invariant lines. But let me link you. I mean, look around on the site in general. Like, I really love the site for everything calculus. The example problems they have are great, and I think it's kind of the best thing that I can like easily give you. No worries. Uh, I haven't seen you do a problem like this, Jed, but this is the original one for what it's worth. It's not posted in my Discord, but Thunder just like DM'd it to me. Thunder also has the answer key. So I was trying to explain, I was trying to get to the same result. You grabbed it? Okay. And then this is the answer key. Thunder specifically asking for part B. There's only one solution that they get in part B. We've gotten two solutions, and I think we're supposed to throw one of them out, but we can't figure out why. But even then, they're supposed to do it a different way than the answer key shows, apparently. Then they're supposed to follow the technique on this site. And so, like, down here in this section, they do some weird stuff with letting things be zero and throwing out. Can you fall outside? Okay. Okay. I mean, if you're, yeah. So I erased a part of it, but from the first part of that, like, second section, you get n equals root 3 over 3. That's the one we have to throw out, though. The one, when you factor this, instead of e equal to 0, you get m equals root 3 over 3 again, or you get m equals negative root 3. And apparently we only keep negative root 3. Let me get out of the way. You're going to grab it. See, I really don't understand what this technique is getting at. And so you could always like guess and check, which Thunder's already said it, like the guess and check does signal that you should throw this root 3 over 3 thing, but like, oh, sure, Jed. In Thunder, yeah. Sorry, in Critical, yeah. Once we're done with Thunder's question. Hello.
Hey, Don. So your X sub kind of confuses me a little bit.
Okay.
So you have an equation for capital X.
Yeah.
Okay, I see. Okay, anyway, hang on. I see what you did there. You just expanded out the negative root 3 over 2. Okay, we're fine there.
Oh, okay.
Okay, so that wasn't it then. And so then you brought everything over and factored out the m's and then the c's, and c is just a constant, right? Except you got that m thrown in there, right? That's the issue that we've got.
Right.
Okay. And so then you've got either c equals 0 or the part on the inside of the bracket 0. And you've got that figured out.
Yeah, and the next stage that you would do is I think you let c be 0. Or the next thing that the website does is you let c be 0, so this part goes to 0, and you only examine this part equals to 0. Oops.
So then you get everything else on the left side is equal to 0.
Yeah, and so either x equals 0, which is trivial, or you factor this, and you get, I use the quadratic formula, and I got m equals root 3 over 3, or minus root 3. And the minus root 3 is what we actually want. We can't figure out why we throw out the other one.
Coming in real quiet. Let's see.
Hey, Kate, Kim Lewis.
Okay.
Understand a similar problem using the same method. Sounds good. Critical. I'll at you in chat.
Screenshotting your work here too, just to have that as a reference as well.
I'm doing good, Kate, Kim Lewis. How about you? Just an revision for the last 14 hours? Jeez, I hope it went well. So I've been looking at this similar... Oh, sorry,
The
what,
other
Jed?
option you had was you were setting m equal to 0, I guess, is the other
Uh,
option. Is that correct?
I think
No.
m should never be 0. Otherwise you'll get a... That's going to be a big part of the invariant line.
Mm-hmm.
Well, maybe you can end up getting 0, but you wouldn't set it to be 0.
When x is 0, though, you get either c equals 0, which is one case, or the part on the inside is 0, which gives c an actual value.
Yeah, I'm confused why x equals 0 is even considered, because x is a variable, and it's more often non-zero than it is 0. That's probably what's confusing about the website.
So yeah, the x being 0 basically means if it's basically looking to see if the point is the whole point of the invariant line is that everything is like, you know, on that line, right?
Everything is on that line for x equals 0?
Is that what it means? It's a point of it's a transformation. Is every point on the line is mapped to a point on the line. That's what the invariant line is. It's, you know, it maps a set to a set, or in this case, a line to a line to the line. And so if you have a point, if you set x equal to 0 as being a point on that line, then you have to figure out, can x equal 0 be a point on that line? And if it can't be a point on that line, then you've got to calculate a c such that, so that you can figure out the value of m. Yeah. It's weird.
Okay, I think that actually might be it, because the origin 0, 0 is always the same under any transformation ever.
Correct.
And so when we let x be 0, we're seeing if there's a non-zero c that's possible also. And I think we just found that there's not.
Yeah, the explanation on the ask Uncle Colin thing, if they used m is negative 1/5, then the equation becomes negative 18/5 over x equals 0, which is not true for all x. Because if you put any non-zero x into there, you don't get a true statement. So therefore, the m equals negative 1/5 can be thrown out as a invalid solution. So therefore, they're going off of the c equals 0. So in our case, if we solve for that part of the, where m was it root 3 over 3? Is that what you got?
Yeah.
So that's 1/2 minus 1 is negative 1/2.
So yeah, Thunder, I think what's happening is this section here, when you let x be 0, is you're checking if there's anything on the y-axis that stays the same under this transformation m. And what this has found is that there's not. C just has to be 0, because when m is root 3 over 3, you don't get any like unique value for c out, is what I'm going with. Or
how did you get root 3 over 3?
Because you let this part equal 0, and you add the 1/2 to the side and then multiply by 2 over root 3.
Root 3 over 2m minus 1/2. Right, so wouldn't you need 1 over root 3?
And that's the same as root 3 over 3.
Okay.
Because 1 over root 3 times root 3 over 3.
Okay.
Yeah.
Okay, gotcha. Yep. I just didn't do the extra step.
Oh, the best viewers are on that website? Okay.
So then when you plugged in, and then you plugged in the root 3 over 3 for the first half of it to see what x would equal. Right. Is that what that bottom line is?
Yes. Because this part we already found is going to be 0 anyway, so I only bothered trying with that part.
And that was true? Yeah, root 3 over 6 plus root 3 over 3 minus root 3 over 2 is 0, right?
Yeah, you just get 0. So it's 0 equals 0, which...
Right.
I don't know how to interpret it. Maybe the thing I was just saying isn't right. Or...
Yeah, and so that's one solution, right? Is m is root 3 over 3 or 1 over root 3, whatever. And then c can be anything we want, and c is 0. So that's one solution. And then the other solution, or was it, no, C wasn't.
C can be anything. Yeah.
Anything. So then what would C have to be if you plug? Okay, I got you. Yeah, C is everything. Let me go back to his answers there. So he's basically just looking for the original statement. Show the invariant point. Find the matrix. You did that. Show the invariant points of the linear transformation M form a line in the plane, stating the equation of this line.
Okay, what happens if we take the solution that is good and plug it in to the entire equation? If m equals negative root 3, then you get x times 0 plus c. Because I think the key is somewhere in the interpretation of this part for why we throw root 3 over 3. So maybe if we plug in the solution we know is good, we can see the difference. Minus 1/2. So that just becomes 0. Minus 3 over 2 minus 1/2. 0. Negative 2c equals 0. So we get c equals 0 from this, whereas this was just 0 equals 0. Like, it's that difference that has to be the significant piece. I'm just not sure how.
So we set c equal to 0 on the left side, and then you calculated m is going to be the same thing.
0 is indeed in fact equal to 0.
I'm,
Yeah.
I'm a little behind on the chart.
Oh, yeah. Sorry, what was the question that you asked?
So you did c equals 0, so you set that whole thing equal to 0 on in the red on the left.
In the red on the left. Yes.
That was the other option that you did, and so in that case, x equals 0 is not true for all x. Or no, if you put x equals 0, then you get that's true.
Yeah, so technically x equals 0 is the solution to that equation, yes. It's just x usually is not 0.
Right. And so then you put everything else in there is equal to 0, and you got m to be. What did you get m to be there? Oh, the two different solutions: negative root 3 over 3, which is the same thing, or negative root 3.
Yes. So from this, we get, maybe the point is that when m equals negative root 3, c equals 0. But if m equals root 3 over 3, we do not get any such value for c. And apparently that means that we would throw it out, but I think the point is that if we let m equals root 3 over 3, like we just don't get anything at all for c. And I think that's the best shot that I have for why we would throw it out. Because over there we do just get one number for c, but on the right we just don't.
Yes, it could literally be anything.
Yeah, and so I'm not sure, like,
the inside is 0.
Yeah, I don't know what the interpretation of c being able to be anything really means. But according to the answer key, you just throw it out. So that's what I'm kind of going with blindly. I still want to see if, like, maybe this thing that you said.
But they didn't do this quite as complicated, did they? They took the. They didn't do the mx plus c route. I didn't, or this is
a different answer key where they do this route, yeah.
Okay. Is that the one we're going off of here?
No, this is a completely different problem.
Okay.
This is the original problem. I don't think it's really that important though. I'm just trying to figure out like this technique part.
Because I guess if we're answering 1b, all they did is set that matrix xy reflects back to xy. But is that
that way? It seems much simpler to me, and it should get the same answer, but apparently we have to do it this other way.
Well, that one, it seems like what they're doing is just saying if you take that transformation matrix on any point, you get that exact same point, not just a point on the line, right?
Yes.
Which is not, because you're looking for an invariant point.
Maybe there is a slight difference there.
Not an invariant line. Am I wrong in thinking that?
Invariant points in their transformation form a line in the plane. I mean, I have no idea why they do a different vector for this way that we've been doing it. It makes no sense to me. I've just kind of been going with it.
Well, I guess, yeah, because I guess y equals mx plus c. I mean, that's the standard form of a line, right? And they're just differentiating between the two x's.
But it should be the same point under the transformation, which is what I don't get.
No, it's saying, okay, so if you got a line y equals mx plus c, right? Then,
sure.
Then given a point x, you can figure out y. So that the second parenthetical bracket, x over mx plus c, lowercase everything, is x and y. And then the right one, where they capitalize X, saying you're going to get a different X on the line, and using the same slope, same y-intercept, you know, X plus B is typically what you use instead of C, but, you know, same thing. Then you're going to get a valid point there. So it's basically saying a point on the line maps to another point on the line when you transform it with this matrix. In the 1B, they're saying it maps to itself. So the solution they get for 1B is showing the point mapping to itself. And in 3, it's mapping to another point on the line. Does that make sense?
I think I understand what you're saying, but I feel like if you're like, basically it's the same, it's always on the line, but maybe you're scaling the magnitude. It's always the same direction.
Well, I mean, I'm trying to think how to reword this. X is just any point, right? And so you got a line X and Y, you know, where it has points X and Y is determined by the value of X. That's, you know, so that's the you know, you got some transformation matrix, and then the point XY, which is defined as X and MX plus C. So that's a point on the line. Then you've got another point on the line, which is capital X. We could call it W, right? And we use the same MW plus C. It's just some other point on the line. It doesn't have to map to itself. It just has to map to something else on that line. And the line is defined as, you take a point, you multiply it by a factor, and you add some add some value to it, and that's your line. It doesn't matter what X you pick, they're all linear. And so the lowercase x and the capital X are two different values on that line. Right?
Sure.
But if you look at the solution for 1B, they're basically saying, take this transformation matrix, apply it to the line, and you're going to get the exact same point, because they're using lowercase x and lowercase y on both.
I feel like that's more in line with what invariant point means, though. It's just weird to me that we would be on somewhere else on the line, but when you say, like, it does seem like that's what's actually happening, where, like, we're always on that line, but we could end up somewhere else on that line.
Yeah, it's a closed set, or what do you want to call it, if you want to go that far, but it's not reflected back to itself.
But I guess it's also going to answer the question of, like, why are we throwing out one of these solutions, I guess.
It's the same reason you throw out solutions that, you know, you throw out solutions all the time when you're, like, checking your answers. So, well, that doesn't actually work. It's a false positive, or what do you want to call it, when you're solving an equation, because you're going to get some imaginary result, which isn't allowed. You know, so when you plug it back in, you say, okay, that doesn't work, so we're going to throw that one out and solve for the other one.
So is there a way to do it without, like, verifying our answers manually? I think that's what, like, Thunder's question is.
This question is from an old paper that uses C equals 0 is always a possible solution. It isn't always a possible solution. Because that article that you were looking at from Uncle Colin, they tried. That one actually did have C equals 0, was a possible, so it did have possible solutions. You could probably come up with a transformation matrix that it isn't, C equals 0 isn't a possible solution.
I guess so.
But it's be hard to engineer.
Yeah, because I oh god, I'm not good enough at linear algebra for this. It's eigenvectors, but we're not allowed to do it the easy way, apparently. We have to do it this really obtuse way that makes very little sense to me. There has to be invariant lines, not eigenvectors, which are, I guess, slightly different. Well, so with this, it's like we've kind of copied this technique here, but like we're supposed to throw out one of the solutions that we got for M, and we can't figure out why. Like, let's plug in the matrix into Wolfram.
Are you doing? So we're going to do alt. That's where did alt 3 come from? What is that? Just a different question, or is that a?
It's a different question that uses the right technique. Thunder was asking about it initially in relation to a different question.
But it's a different matrix.
Oh, thank you, Zach. A different matrix, yeah.
So it's a completely different question, but it uses the same technique.
So yeah, this is the original question that Thunder was asking about the work is on the board for.
Mm-hmm.
That Zach asked to see, I think. Or, I mean, I could show the prompt for the answer key that we were looking at. But for the question that we've been working on, that's the original prompt. The other one? Oh, okay.
Yeah, I didn't see this one yet.
Because if there's only one invariant line, I assume we have one repeated eigenvector. Or no, you never have a repeated. You can have a repeated eigenvalue, but not a vector. Is that why this is weird? Is the y-axis one of them? Right, finding eigenvector 1, 2, in this really weird way. They get y equals 2x. What are the eigenvectors of this? Oh wait, oh, this is for the... No, oh no, I wanted the eigenvectors... Oh my gosh. I have like... I want to look at the eigenvectors for the other matrix. Okay, here, look. I'm going to drag this window away. That way you can look at that all you want, Zach. Because I want to work on Wolfram Alpha for the other matrix. Square root 3 over 2. Square root 3 over 2. You're kidding me. 1 over root 3 is an eigenvector. Or it makes one. Oh my god. Why isn't it an invariant line? Okay, look. The original matrix M that you sent me originally. Actually, I don't think it's easy to see from stream, right?
1/2, yep.
Eigenvectors. Root 3, comma 1. 1 over root 3, negative comma 1, which the negative sign, I don't think it matters. So why is there no invariant line associated with that eigenvector? Are they the same line? Is that it?
Go back to your eigenvectors again. I mean, they gave us the...
Are they scaled different? No? Or not?
1y and 1 to n. Ooh.
Different people want to see different screens, Zach. I don't know what to do, and I want to see screens too.
Picture in picture.
I guess so.
Yeah, if you were to multiply that first one by root 3, just scale it up by root 3, you'd get what?
You would get 3 comma root 3, but I don't think you can scale like
down,
this one to get the other one. The signs are opposite. You're never going to get the exact same one.
V1, divide that by root 3, you get 1 and then 1 over root 3, which is one of your answers, right?
I don't know what you just said, to be honest.
You divide both coordinates by root 3?
No, that doesn't get you... Like, the one has to stay the same, but the root 3 has to change is the issue. You can't change, like, just one. And even the one has a negative sign and one doesn't. Like, one is negative positive, the other one is positive
No,
positive. You can't scale
okay.
these to be the same. So they're distinct. Like, you should always
Yeah,
have
there's two
distinct
different solutions.
eigenvectors.
But the solutions you got were √3/3 time
and √3. So both of those would lead to
go back to your
the eigenvectors that Wolfram alpha gets. I don't know, like, how are there not two different invariant lines? Did you see my comment for 1C? I don't know, Zach, you're sending too many chats. I can't keep track. I just asked people who are trying to help me, I guess. Let me go back up and read it. The comment for 1C. The assumption that the line mx plus c is invariant, that c equals 0 is true. I saw it, but I didn't know how to interpret it. If is that, or 1c multiplying the eigenvector 1, 2. How do we know the line is through the origin? Yeah, sure, Zach. That would be helpful. If you can join the waiting room in my Discord.
Well, I mean, we know that it goes to the origin because we proved that 0 was a reflective point, and all the points on the invariant line would be collinear.
Oh, hello, Zach. We can't hear you. That's weird. Still can't hear you.
Are you plugged in?
Try that.
There we go. Hey.
That should be good. Okay, so I'm looking at your, so I think the point here is that the eigenvector has to go through the point 0, 0. Yes?
Yes.
And hence C must be 0 in this case. So you'd have to, whatever that's, the 5m minus 8, since that's not going to be 0 anywhere, the other thing has to be 0. Like there's some kind of, I think that's what this is trying to argue.
Why do we ever include this C in the first place, though, if it should always pass through the origin?
That's the point. I think that this is just I think it's rather silly personally, but
okay.
You could have just solved this with M and I think it would have been fine. But I think the point is to be as general as possible. I don't know. Let's look at...
Okay.
We can look at your other one, though.
So, like this one, Thunder is supposed to use this technique down here, apparently, for B. We're supposed to use a technique from the other one, but yeah, this is the one that Thunder was actually asking about.
Sure.
So the answer key gets only one of the possible values for M, and we have to know why we throw out the other one. So the minus √3 is good. We also get 1 over √3.
So √3 and 1 over √3? Is that what I'm hearing? I know, Stu,
yeah.
I'm with Stuki here. It's very silly.
Okay, I feel a lot better about this.
This is not a... I know, I'm not loving this either, but I think the point here is that you've got the √3 over 2y equals 3/2 x. I'm looking at the solution for B. And then you have 1/2 y equals negative √3 over 2x. That's just... I'm writing this out on my paper. Negative √3 x equals y, and √3 y equals 3x. Yeah, they're basically... So, one of
basically
these
the same
is...
line, aren't they?
One has a negative sign on it, which is important. And if you go, can you go back to Wolfram alpha?
Oh, sure.
Apparently, invariant line for them means pointwise fixed, rather than fixed as a set. And because of that, only eigenvalue of 1 is... Oh, that is stupid. I think because, oh my gosh.
Was the problem just designed to be this
Well,
stupid,
the two, so I'm getting the same thing that Wolfram gets. So I have the exact same thing on my paper. If you simplify all that stuff that was on the answer key down, that's fine. But I think what Stuckey's talking about is that a line of invariance, and correct me if I'm wrong, Stuckey, is it that we're talking about like a reflection line? A line of reflection type thing? Or like where you have a I
don't think it's a reflection necessarily, but more that every point on the line maps to another point on the line when transformed.
Yeah.
But it's not necessarily
yes, exactly.
A does A implies B does not mean B implies A.
That's what I meant. Thank you.
Yeah.
Yes. So every every vector is mapped to itself. Right? That's how I'm interpreting.
In the solution for the original problem, it looked like yes, it was mapped to itself, as opposed to being mapped to something else on the line.
Right.
That's the point I was trying to make with the difference between the lowercase x and the capital X.
And I think that's the point with lambda equals 1. That's the interpretation of lambda equals 1, is that there's no scaling along the vector.
Why are we keeping the solution with lambda as -1, though?
Those will reverse direction, right? All point-wise fixed line satisfies mv equals v for all equality on the line. Yeah, so I think that's what Stuckey's saying, is that you're mapping v to itself, like literally to itself. That's what invariance would mean. And so we don't care about the -1 case, because that would change the direction of our vector, still keeping the same line.
Yeah, I mean, if you look at, again, looking at the problem of the solution they gave, they're using x and y in both the left and right side of the equal signs in this particular problem. But in the other problem, they were using mx plus c and capital X plus c, meaning it maps to some other point on the line, so there's a different solution there, right? Because if you're mapping x to x and y to y using this transformation, it's self-reflecting.
Well, self-mapping, like we should,
like
identity map, basically.
Yeah, identity.
It's not the identity matrix, but you're basically mapping things to themselves along this line only. Donna, you have this look of confusion on your face as I'm watching.
Because...
I want to.
I mean, I guess Hunter's the more important person, but lambda equals -1 goes with root 3, 1 for the eigenvector, but that's the one that they keep. Shouldn't we want the lambda equals +1? That's not the one that the answer key uses, though.
The solution key. Okay.
It specifically gets the -1.
The solution key keeps the -1. Yeah, that's correct. So it kept the lambda equals 1 case. That's correct.
No, that's lambda equals -1, isn't it?
No, look back at the solution. The solution says that the first eigenvector maps to the lambda equals -1 case. The eigenvector here is the slope of the line.
It's the slope of the line.
Right? You're talking about the direction of all the vectors, and the direction of all those vectors is the slope of the line. Yeah, what's Stuckey saying? Exactly.
Oh.
Compute the slope of that line.
Oh, it gets flipped. Oh my god.
Yeah, there you go. Thank you, Stuckey. That was much. You did better in chat than I did in voice call. I feel. I tried.
I'm just here for moral support.
It takes a village. I guess that's what I'm learning here, is that.
Okay, so I guess maybe we understand it now. I'm not sure what to tell Thunder, who doesn't get to use eigenvectors or eigenvalues.
But the principle's the same here, is that you want to... An invariant line literally doesn't change. Like, when I apply a matrix transformation to an input, I get the same output that I got as an input. That's literally what invariant would mean, right?
Right.
And so I want that to be true, the only way that can be true is if is essentially where x equals y. So if we use the reasoning given here, my input is xy, my output is xy.
Okay, and so if with the system equations that we got, the issue for thunder is that if we have 1 over root 3, you get like a statement that's true for all c, but we need c specifically to be 0, like with the negative root 3 case, I think is the point.
Mm-hmm. Yeah.
Because otherwise we're not necessarily mapping straight back onto like the exact point, I guess.
Is there a distinction between an invariant line and a line of invariant points?
I feel like only
an invariant line
feel like the same thing.
A point on the line maps to another point of the line. A line
Right.
of invariant points is a line formed by a bunch of points that map to themselves.
Yes.
But they're not identical. A line of invariant points is a special case of an invariant line.
I would just personally, I would just use eigenvector and eigenvalue.
Same.
Personally,
I'm sorry you have to do this, Thunder.
I know, I do too. Yes, just making this distinction. Yeah, so like Stuki agrees.
So
I don't like the notion, like the way you have to sort of contort English, the way you just did that. I don't personally like it. Not that you're wrong, but
I'm finding articles about like, you know, if an invariant line is a line where every point maps to another point of the line, is there a special case where every point on that line maps to itself? And that's where I found this term called a line of invariant points. So it's not something I'm making up. It's something that's...
I believe you. I'm just saying I've never heard it said that way before. So I'm just trying to get my mind around what you're saying. Again, you're not wrong. I think you're right. It's just I had to sit there and really like mentally do some mental gymnastics.
Sure. Is this going to be the next class topic? And who's teaching that one?
It's going to be Don, right?
Oh,
because Don was the one talking through all this.
He's doing physics right now and magnetism, and
I'm taking infinite series in the fall, so I got one already, but I'll keep it in mind.
Danny, Danny, what are you teaching?
Yeah, Danny, what are you teaching?
Oh, I want Philosophy 101 from Dan. And Wizard, or no, Wonderful 101.
Wonderful 101, that's right. Oh, gosh. Well, I hope that helps.
Yeah, things are helping on, Zach. I was really lost with this. I still feel a little lost, but I feel a little more guided now.
All right. We'll be in chat.
All right. Thank you, Zach.
Indeed.
And thank you, Jed. Okay. Oh my gosh. So yeah, hey Ben. We're doing it in a very obtuse way. Yeah, but it's unfortunately the same problem. You can find eigenvectors, Ben, using the definition of an eigenvector, which is like it doesn't change. Like you have a linear transformation, multiply it by a point, and you should get the same point back out, and you solve the system of equations. But the wording on it is super stupid. So the issue with so the Thunder, I'll try to explain it. The issue is for m equals root 3 over 3, okay, let me... How should I draw this? That's one eigenvector. That's the other eigenvector. For m equals root 3 over 3, which is the bad one, if you a point on this line, let's just say that's m equals 3/3. This is probably not at all graphically accurate. Like the point is on this like eigenvector, things get scaled different. It's not quite the same point. So like if it'll stay on the same line, I think. So like if you take that vector there, it might get scaled like shorter and even reversed or something like that. Whereas on this other one, if you plug in something on this eigenvector, you'll get the same exact thing back out, I think. So they are both always on the same line, but we only want the one where we're at the same exact point and not any scaling differences. And the difference between them was that for one we got c equals 0, the other one we did not get c equals 0. But I have a really hard time connecting like those two things exactly, but I think that's like the pattern that you could use. Not sure exactly, but reverse. Okay. Same size and reverse. Okay. So yeah, I was assuming it could be a different size, but if it's the same size but reverse, I guess like it's not the same exact thing, which is the issue, regardless of what that difference is. I think you know which one is which with whether you get c equals 0 or 0 equals 0 or c like. The bad solution is true for any value of c you want. The good solution is only true for c equals 0, and that's what we do want. So you could even start this problem with, I think you could even start the problem with the quadratic part. You shouldn't assume c equals 0, you should check whether c equals 0, I think. For this technique. You want to keep the plus c, but you could, I think the point is you could start with this part here, get your two possible solutions, and then do like this exercise over here or here and see what you get for c. So c equals 0 means -√3 works. M equals -3 gives us c equals 0, which means it's good. M equals 3/3 does not give us c equals 0. C can be anything, so that's bad. We want c to be 0, I think. Yeah, no worries. That's at least my interpretation of the conversation that's happened. And for some reason, you still keep coming back and asking questions, which I appreciate. And I know you said something about vector projection as well. I might have a quick way to explain the idea that might make sense, but I don't know. If you want to like call it there and not think it anymore, that's cool too. I never had to do calculation like this, Jed. We just got to do it the easy way. I don't know why Thunder doesn't get to do it the easy way. You asking me a different day? Okay, sounds good. And honestly, big shout out to Zach or Eats the 2i Pie and E&M Studying, both of who could probably explain it better than me as well. Although I'll definitely try if you ask me. Oh my god, what a question. Thank you, Thunder. Hey, Box, yes. I think we got to the bottom of it. It took 3 math streamers and Jed. We did get there eventually. Okay. Yeah, Jed, that yeah, it was definitely good that we took a break to get to Zappins. $10. It was confusion. You should be glad that you missed it. Man, I don't want to like reopen the whole can of worms, but basically, you multiply the, or you find this matrix M that represents the linear transformation. The way to find the invariant points of that linear transformation, and we are not allowed to use the normal eigenvector eigenvalue calculations. You have to do it with a system of equations. Well, actually, you could even do this way, which makes sense to me. You had to do it this other obtuse way. That's super weird. For every 10 subs, you go out in public with a middle school math problem. Like I solved the problem in public, Viv, or what does that mean? Oh god, I hope we didn't take too long. Critical had to go. Ask people to solve them. Oh, that's I'll ping Critical on Discord too. Oh, you're here. Okay, cool. Gets $5, so you make $45. Oh yeah. Rotation and a reflection. Okay. Well, yeah. Even then, like 50%. Like I never actually get 50% because of like taxes and or like even before the money gets to me, taxes get taken out for like the country, and then I would also pay income taxes if I made enough to get taxed. Yeah, exactly. Exactly that. And I pay income taxes. Yeah, no, and if they're in like we looked it up for like Turkey once, and that's like 10 cents in American dollars. A sub over there is what they pay. Something like that. All right, so critical. I see we want the arc length of a parametric equation. I need to look at the formula for this. There we go, arc length of parametric equations. Oh yeah, it's just this formula. And they give us everything that we need to know. Oh. Okay, well, it is just this formula. I don't think we're gonna get a very... It's gonna be annoying integrals in it. I think we're gonna get some Pythagorean identities. We're gonna get some ones involved here. Okay, so it's gonna be just applying this equation or this formula here, critical, but yeah, exactly. It's not hard, it's annoying. This is not hard if you know like what to do. Okay, let's erase the board. Oops, left little line on the right side there. Okay. Okay. So, the internal form is quite pretty. Oh, good. Yeah, I mean, we could apply some triple angle or stuff here, but I don't think we want to go there. We're definitely going to get like some sine squared plus cosine squared stuff. X equals 3 cosine t minus cosine 3t. I said it and I already forgot it. Was it this? I have a memory of a goldfish. Okay, yeah, that's good. 3 sine t minus sine 3t. Zero is less than t is less than pi. So they give us the bounds of the integral directly here. So what we want to do is plug into the formula alpha to beta root dx dt squared plus dy dt squared dt, where alpha and beta are the bounds of t, and we have to figure out what dx dt and dy dt are. So let's do that first. So if x is that, dx dt, 3 cosine t derives to minus 3 sine t. We have to use chain rule on this one. Oh! Wait. Negative sine t, but it's minus, so we get plus. Is that? Oh, wait. Okay, no, never mind. It's... I was wondering if you don't see the cancellation. It's 3t. There we go. I was like, doesn't those add to 0, but this t and 3t. Okay. So that's a dx dt. Dy dt is 3 cosine t minus 3 cosine 3t. All right. So no dx dt, we know dy dt. Differentiate. I don't think I even said to derive their pen box. Are you just doing that for good measure? I think I was saying find dx dt and find dy dt. So maybe that's our happy compromise. All right. So that's dx dt and dy dt. Oh no, I didn't say derive. You're right. Let's plug into the formula here, and this is where things are going to get a little ugly. So 0 to pi are the bounds they give us. Minus 3 sine t plus 3 sine 3t squared plus 3 cosine t minus 3 cosine 3t squared. All right. Product to sum. Yeah, we're definitely going to need that, Zach. So the unfortunate thing here, critical, is I don't see an easy way to avoid multiplying this out and multiplying this out and looking for identities. We are going to get some identities, but we don't have a simple trick to make this really easy. We just have to go through a lot of pain as far as I know. So I'm going to multiply out this squared. So we do this squared is 9 sine squared t. We do that times 2, which is minus 18 sine t sine 3t, which that's what exactly we're needing the sum to product for, or the product to sum, which we're also going to need for the cosines, but we'll deal with that later. And then this one squared. It's 9 sine squared 3t. I'm going to need 2 lines here. Plus, and then we're going to come over here for the cosines. That one squared. 9 cosine squared t, that times 2, minus 18 cosine t cosine 3t, plus that one squared is 9 cosine squared 3t. Terrible notation, but we'll go with it. I don't want to mess with triple angles if I can help it, Jed. Triple angles kind of scare me. If you see they lead to some nice simplification, we can look at that too, but I think triple angles would be worse than doing this. All right, so the good news here, Thunder, is we have a 9 sine squared t and a 9 cosine squared t with a plus. So I'm going to use the Pythagorean identity. Sine squared t plus cosine squared t equals 1. We do have 9s here, but you can multiply both sides of this equation through by 9. So we have a 9 sine t squared plus 9 cosine t squared, which you know is equal to 9. So let's just write that. And similarly, we have a 9 sine squared 3t plus 9 cosine squared 3t. And you're allowed to just sub whatever angle you want inside this Pythagorean identity. It's always true. So we also know 9 sine squared 3t plus 9 cosine squared 3t equals 9. So that plus that is just 9. So I'm going to say plus 9 again. Now we have to contend with sine t sine 3t, cosine t cosine 3t, which aren't as simple. Ooh, we don't need product to sum, as it turns out. If I see a different idea that we can use here. Oh, I do mean critical. Yeah, thunder here. Okay, I feel like I've been saying thunder this entire time. I mean you critical. There's a clever thing that we can do here, though. It's not going to be as painful as I thought. Futurama reference? Oh, yeah. The best kind of correct. Hey, Zone. All right, let me get this trig identity. Because this is a trick that I love using. Okay. It doesn't usually work, but there is an identity. Cosine theta. What letter did they use there? Like phi? Yeah, phi. Oh, sorry. It's shoot. Is it? Yeah, exactly. That one, Viv. Plus minus. Okay. I have a really hard time memorizing these. Actually, God, see, I'm copying it down on the board here. I just had the memory of a goldfish. It's really hard to spot this trick if you haven't seen it before. I'm writing down the general identity, and then I'll write it down for our specific case here. There we go. Okay. Make sure I copied it down right. Okay, good. I know, Zach. We can use it here. Sorry, I'm taking it like because I'm excited because I like using this trick. I feel like I sounded annoyed, but I'm not. So we can. What we have here, I should rewrite this. So 9 plus 9 is 18. Each of these have an 18. So I'm going to factor the 18 out. So that becomes 1. Let's factor a negative 18 out, because these have the same sign. I think it's going to make it a bit more clear what's happening. Sine t sine 3t plus, oops, cosine t cosine 3t. Okay, so we need to set it up right. But I notice here that these angles follow the same pattern, and it's cosine times cosine and sine times sine. So we kind of have the right side of the formula here if we rewrite it a bit. If we have cosine t cosine 3t plus sine t sine 3t. These have to have opposite signs because one is plus minus, the other is minus plus. So can we say that this is t minus 3t? That's the trick here. And I think this is right. And so t minus 3t is minus 2t. And cosine of a negative number is also cosine of a positive number because it's an even function. So this entire thing here is cosine of 2t. It'd be much simpler than doing like product sum here, product sum here. It would come out to be the same thing, but this is a trick that I really like spotting the right side of this identity here and making it into the left side. What is it called? Oh wait. Product to sum, sum to product. I might have misunderstood what you were saying before, Zach. I'm sorry if this is the trick that you saw. This sheet that I'm using calls it the sum / difference identity. This right here. So it's the same thing that I copied down on the board as well. But yeah, there are other ways to approach this too. I think this way is the simplest though, if you see the trick. So what we can say now is that I hope we're not getting square root of a negative number here. Minus 18. We said this entire thing is equal to cosine of 2t. dt. Okay. So this negative sign out front, it just kind of messes with my brain because I don't want to take square root of a negative number. I assume this entire thing doesn't come out to be negative, but what I'm going to do... What? Yep. Oh, Euler's compound angle, interesting. Are we going to double? I don't know where we're going to go with this one. Is that helpful, though? 1 minus... The 1 minus is gonna... Oh! I see. Okay, yeah, you guys are right. You're both right. We could use either of those validly. I'm gonna rewrite this first, though. I want to get this into a simpler form. I'm gonna multiply the negative sign back inside here, because it just kind of scares me. And I'm going to bring the root 18 out front. I'm going to like give it its own square root here. So the negative sign comes back inside here. So we get 1 minus cosine 2t. This just looks nicer because having the negative sign out front and the square root just kind of scares me. I don't want to have a complex variable. And now I'm going to apply... We're calling it a double angle or a half angle. I don't remember what it's called. A double angle. Cosine 2 theta. Yeah, we'll keep things with cosine, I guess. Cosine 2 theta equals 2 cosine squared minus 1. So I'm going to use another identity here, which is cosine of 2t equals 2 cosine squared t minus 1. Called a double angle. I think the sine one is fine too, though. Oh no, I guess the sign is different. Yeah. 2 cosine squared minus 1. Okay. And is that going to work out here? We get 1 minus... No, we don't want the sine one, don't we? Let's try them both. So there are multiple formulas for cosine of 2t. We want a specific one. 1 minus 2 sine squared t. I'm debating between using this form or this form, depending on the sign of this one here. Because I specifically want one of these ones to cancel with the one there. Is the thing that I'm trying to work out in my head. root 18 is 3 root 2. We definitely want the sign. Because we want 1 minus 1. Okay. Three root 2 root. We get 1 minus 1 is 0. Minus negative 2 becomes positive 2. Okay, cool. So we're nearly there. This is the hard part of the integral done with. We just need to follow it through now. I hope I'm not being covered by the problem. Okay. So yeah, I'm going to split this 2 times sine squared t up to have their own square roots. 3 root 2 times root 2 times root sine squared t dt. I'm going to start going to the right now. Root 2 times root 2 is just 2, and 3 times 2 is just 6. The square root of sine squared is just sine. Technically, it's the value of sine, but we don't care. It's like, technically the square root of something squared, you should put absolute values, but sine's always positive over 0 to pi, so who cares? Positive or 0. dt. Okay, and we know how to integrate sine. Because the 6 is just a coefficient, it'll stay the same. Sine integrates to negative cosine. Cosine t divided from 0 to pi. Negative 6. Cosine of pi is negative 1. Cosine of 0 is positive 1. So we get 12. Is that what Wolfram said, Jed? That's the link? Okay. Yeah, I really love using that trick with cosine, or like the add or the sum and difference identities. I get excited. I just feel super clever, even though it was shown to me. It is. Oh, you can just type in the length of the curve? Oh, that's nice. It is 12. No worries, Critical. I almost called you Thunder again. I was literally reading your name, too. This reminds me of the thing in the Metroid games, like the jellyfish things. I guess it just looks like a jellyfish in general, like the top of it. Love hate trick identities. I hate remembering them. Aren't they really called Metroids or something? I don't know. Okay. But yeah, I hate memorizing the identities, but like that trick there, I love, because otherwise I was gonna do these formulas here, and these are terrible. Well, they're not. It wouldn't be that bad. It would still simplify to be the same thing, but like it saved a lot of work. No. Metroid is the name of the main character. Those jellyfish things are called Samus, okay? What if Samus was a girl? Thunder, do you still need help with any ones that you posted like the past few days, or can I like mark those as answered? No, Critical. Did I say Thunder again? Thunder, you're living in my head rent free. Dude, I can't. Did I say hi to Anders? Hi, Anders, if not. um. Okay. Yeah, you are. That's what got my brain so big. It just filled up with thoughts of you, Thunder. And like agonizing over how to explain vector projections when I only have like a basic understanding of them myself. Oh, wait. This is an, do we have to unparameterize this? Or can we cut straight to the chase here? Oh, really, Zach? Yeah, in general, we were trying to, it was a big problem that came up that Thunder asked, but it kind of evolved in trying to explain what a vector projection actually is. Yeah, because it came from a mechanics problem that Thunder had with the ball bouncing off a diagonal wall. And it involved getting the component parallel to the wall and the component perpendicular to the wall. And that's what I was having trouble explaining a little more theoretically. But if you do, like, I assume it'll be too late for Thunder by the time you get started, but like, if you post the VOD, I'd have to like make sure I send it over to Thunder or something. The vector projection without the projection. Yeah. Yeah, we weren't allowed to use the actual projection. Yeah, they were cutting straight to the formula of a vector projection without calling it a projection. So it was actually the exact same issue that we're having with eigenvectors. We're finding eigenvectors without actually calling them eigenvectors. Can we do surface, not volume? I was going to do volume again, and I think I made that mistake with you before, critical. Yeah, we can just do surface area direct to the parametric. Oh, we just slam a 2 pi y in front. I can send you the problem where it came from as well, Zach. I don't know if it'll make... It's something that I've seen you like do all the time, but if it helps to see like the context. You have to go. All right, sounds good, Thunder. Okay. So critical. It's going to be nearly so for the surface. It's nearly the same formula as we just used in that last problem. But if you're rotating about the x-axis like we are here, we have a 2 pi y in front. If they're rotating about the x-axis, we have a 2 pi x in front. But other than that, it's basically the same thing. Okay, so you understand that part. I assume the actual integral maybe then is what you're asking about once we set that up. For the Wolfram. Okay, thank you, Jed. Let me downscale the problem a little bit. X is t cubed, y is t squared. 0 is less than t is less than 1. About the x-axis. So since we're about the x-axis, the formula we want is going to be from 0 to 1 to, oh god, 2 pi x dx dt squared plus dy dt squared dt. So let's plug in 0. We know x is t cubed. Dx dt is 3t squared. That's just power rule. Dy dt is 2t. By power rule again. Oh! Is this a trig sub? Man. This is a trig sub. Is it? I don't see a U sub that we can do. 2 pi y? Oh, dang it, you're right. Oh, is that gonna... I think we solved the issue. I think it's still gonna be a trig sub. Thank you for that, Fembox. How to determine which variable is going to be here? Critical. Obviously, I'm having trouble with that, but it depends if you're rotating about the x or the y-axis. So they're in here. They're asking us about the x-axis. Yes, we do want y, and that's just how the formula goes. Oh my God, Fembox, I'm doing everything wrong. You're right. So yeah, if you're rotating about the x-axis, you use y. It's whatever the opposite is, I guess. If you're rotating about the y-axis, you use x. And that's just, I guess, something you have to remember. Thanks for that, Jed. I always forget. Okay, now I also forgot to square the derivatives. The differentiations, one might call them too. You just write it off to the side here. Just dx dt is 3t squared. Just dy dt is 2t. But it's dx dt squared and dy dt squared, which is what I forgot. So 3t squared squared is 9t to the 4th. 2t squared is 4t squared. Well, I immediately see we can factor a t squared out from the inside. So let's start by doing that. And now that's square root of t squared, which is just t. So we can bring that t squared outside. So this is going to be t cubed now, because it's getting multiplied by just t. Times 9t squared plus 4 dt. Can you use sub work on this? It might not be pretty. A trig sub might be necessary, even if I do a U sub normally. Hey Bode, a physics test tomorrow? You can try, Bode. Depending on the physics question, I don't know if I'll be able to do it. Zach, you said yes. I don't know what it's like. I was wondering if like we can somehow make this U sub work. I don't think it will. Maybe it can. Let's just try this U sub. I have a feeling that we're gonna get something that's still tricky, but we can potentially avoid having to do trig with this. I don't know that though. So if we take u as 9t squared plus 4, du is 18t dt. So we're basically dividing out in 18t. 2 divided by 18 is 1 over 9 pi, just t squared now, root u du. I'm dropping the bounds for now. And we can figure out what t squared is in terms of u, because if u is 9t squared minus 4, then t squared equals u minus 4 over 9. Ooh, okay, yeah. This is good. U minus 4. I think we get a square root or something weird. Okay. Make sure to multiply by 2. Did I not? Did I miss multiplying by 2 somewhere? I dropped the 2. Well, it was 2 pi, but I divided in 18, so it became 1/9, right? Or is there a different 2 that I dropped? Oh, okay, cool. All right, so I'm gonna, okay, cool. So this is gonna be much easier to integrate than what I had in mind. Okay. So 1/9 pi and the 1/9 on the bottom of the fraction there are all constant coefficients. They can be shoved out front of the integral. So I'm going to call it pi over 9 times 9 is 81. U minus 4 times root u du. Okay. If we multiply this root u in, we're going to get something that we can integrate directly, which is great. Not ready to integrate yet, though. We get u root u minus 4 root u du. I'm going to go one step further before integrating. Make sure I'm not being covered up by the problem. I'm not? Okay. U times root u is the same as u to the 3 over 2. And I'm writing that to make the power rule a bit more clear about what's happening. Similarly, root u is the same as u to the 1/2 du. Now I'll actually go ahead and integrate. So power rule on u to the 3 over 2, we add 1 to the exponent and divide by it. 3 over 2 plus 1 is 5 over 2. So we divide by 5 over 2, which is multiplying by 2 over 5. U to the 5 over 2. 1/2 here plus 1 is 3 over 2. So we're going to multiply that by 2 over 3, which is 8 over 3. U to the 3 over 2. Now let's unsub and plug in our bounds. U we said is 9t squared plus 4. This is not pretty. What is this? No twos were harmed in the working of this problem. Hey, Y8, by the way. All right, so we don't have pretty numbers. Oh shoot, I'm being blocked by the problem a little bit. Is that being blocked by the problem? No, we're good there. Wolfram means a trig sub? Well, obviously we're better than Wolfram here. We're able to avoid one. It should be the same result though. Okay, what the heck does this thing turn into? 2/5. So we're plugging in 1. So 9 plus 4 is 13? What? No way. Did I do something wrong? How would we get 13 to the 5 over 2 and 13 to the 3 over 2, right? When t equals 0, we get 4, which does evaluate cleanly. Thankfully. Ugh. 13 squared root 13. Oh, Penbox, if you save me from doing physics, then like, thank you. I'll still take a look at the problem, but... So yeah, that is 13 squared root 13, like Zach says. 13 squared is 169, which I have memorized because there's 69 in there in Teehee. 169 times 2. 338? Because 170 is 340? I'm just gonna say 338. Try and stop me. Root 13 over 5. 169 times 8. Oh, I'm not doing that in my head. Oh, wait, no, it's just 13. I'm correct? Oh, hell yeah, Jed. Wait, critical. This thing that I was saying here was sort of 13 to the 5 over 2. And 13 to the 5 over 2 is equal to 13 to the 4 over 2 plus 1 over 2, which is 13 to the 4 over 2 times 13 to the 1 over 2. This is probably maybe more information than you needed, but you can rewrite 13 to the 5 over 2 as 13 squared times root 13. And so I was doing 13 squared is 169 times the 2 that was right there to get 338. Now we can deal with the 13 to the 3 over 2 in a similar way, except it's just 13 root 13, and 13 times 8, I think Zach said, is 104. 104 root 13 over 3. So terrible numbers, but we sure got them. Now over here, 4 to the 5 over 2, let's start with the square root part. So 4 to the 1/2 is 2. Now 2 to the 5th is 32. Times 2 is 64. Then distribute the negative over here so that becomes plus. 4 to the 3 over 2, well, you square root 4 is 2. Now we cube it is 8. 8 times 8 is 64. Dude, these are terrible numbers. I'm giving this to Wolfram. Watch that sign? The sign? What's wrong with the sign? It's minus a negative. Oh, okay. (336 root 13) critical. That's what you're written as minus. Oh, okay. Cube it? I didn't see where that was. Which I did write that part a little bit messy. Like, are you talking about that line right there? It's 338. Times root 13. That's marginally cleaner, still kind of messy. Sure, Jed. I mean, I'm too lazy to simplify it, but... Well, I'm going to plug in the thing that I wrote on the board first to figure out what it simplifies to, and then I'll look at your answer link. Wait, pi over 81, 338 root 13. I'm a bit off? No. Say it ain't so. I will not go. Turn the lights off. Carry me home. Get 4.936. 4.936. 1/81, 128/15. I think these are the same answers, just look different. The numerator is divided by 2. The volume answer? Oh, okay. The volume answer is clean? Where's the volume? Oh, yeah, 3π/7. That's nice. All right, so Critical, I phoned it in for the very last step because I was just gonna. What did I just do? What? What are you doing to me, Wolfram? Okay, there. Because I mean, if you simplify my last line there, you get common denominators for things. You'll get this. And I just didn't want to do that step, but I think this answer matches with, or you could also put it in this format too. But these answers do match, so I think the technique here is right. So yeah, that was a pretty difficult integral too. Yeah, I care more about showing you the actual technique to integrate it. So let me know if you have any questions on that. I hope that you'll be able to follow through with like getting common denominator and just like doing that number crunching. It's really annoying, but yeah, the hard part there is the integration, I think. Looks like Bode, you got what you needed. From Finbox. Okay. Sounds good. I think I would have actually been able to do this physics problem too, but if I don't have to even think about it, that's even better, I think. No worries. Critical. Oh my, they're taking G as 10 meters per second squared? That's weak. I'm just looking at this for fun. So no need to pay attention to Bode if you don't want. What is H? G is 10, pi is 3, C is 1 foot per nanosecond. Gravitational constant isn't so constant. Oh yeah, sure, critical. That's probably more important to look at. Ooh. Ooh, what's happening there? Yeah, I think I can see what you would do, but I won't bother looking at it while there's other questions people still need help with. Find the exact area obtained by rotating the given curve around the x-axis. So I thought it was going to be proving the volume of a sphere, but we actually have cubes. So, okay, I'm just kind of curious. I want to see what the shape is. This isn't really relevant to the actual problem critical, but I'm just kind of curious what this graph comes out to be. Cosine cubed t sine cubed. If I can't figure out how to do parametric equation decimals again, then I'll leave it, but oh no. Ugh. 0 is less than t is less than pi over poo? Pi. Really? What is it if it's 2 pi? Oh, it's that thing. Okay. Okay, sorry, I was curious what this thing actually graphs out to. It's just that little like piece of the star though. We're rotating about the x-axis. Okay. The graph doesn't actually like affect what we do here. We're just gonna plug it into the formula. About the x-axis. Okay. It's called an asteroid? Not an asteroid, but an asteroid? I remember seeing you having a problem involving that a while back, Zach. Not from the source? Oh, okay. Does that problem stream? Oh, okay, yeah. Astroid? Oh, it's pronounced like that. Standard computation time exceeded? Ooh, okay. Well, it's probably because of the A's. That might be messing up Wolfram. Zero less than theta less than pi over 2. You can provide the answer. That sounds good. It's fancy tops. Oh, yeah. 3 over 8 pi a squared. Ooh, all right, let's see if we get that. So we're rotating about the x-axis, which means we want to stick a y in front of the formula here. And just like last time, I'll fork out dx dt and dy dt over here. This integral is going to be hard, isn't it? 3a cosine squared theta chain rule. Cosine derives to minus sign, differentiates to minus sign. Am I doing something wrong already? Oh, okay. Yeah, I am. No, the integral bounds are right. I just didn't finish writing them. This is clearly a pi over 2 and not a 1. It's you guys who were wrong, not me. No, you're right. Thank you. That derives to power rule first, 3a sine squared theta, chain rule cosine theta. Oh my, clearly, yeah. All right, so we know dx dt, we know dy dt. Y is a sine cubed theta. Oh, you guys didn't even correct my variable of integration. Wow. We're doing everything in terms of theta. Theta, theta. Okay. All right, yeah. You hadn't gone there yet? He's blaming chat. It's a variable, it can change. There you go, Jed. I prefer your way of doing math. Oh god, and I do not like this way of doing math. We gotta square this thing. 9a squared cosine to the 4th theta sine squared theta plus 9a squared sine to the 4th theta cosine squared theta d theta? That's what we're up against here? Oops. Square has gone too far. Okay. Well, let's start with factoring the 9a squared out, because that's going to be able to get, that's a perfect square. So just like I did in that other problem factoring out the 18, I'm going to factor out a 9a squared, and it'll get square rooted on the way out. So the square root of 9a squared is 3a. We have a 2 there and an a there, so it's going to become 6, because 2 times 3 pi. A times a is a squared. Sine cubed theta. All right, now under the square root, I see these have a sine squared, cosine squared as common factors, so let's try pulling those out. What about this inside? A cosine squared? Oh, that's just cosine squared, and that's just sine squared. How convenient is that? This isn't actually as bad as I thought it'd be. Well, we're going to have an annoying integral after, but... where the radicals are curved and pi over 2 equals 1? Yeah, 2 is the real approximation for pi. Forget about 3. 2 is much easier to work with. I'm going to pull the constants out front. 6 pi and a are all constants. Sine cubed theta. All right. Now here's where the magic happens. Cosine squared theta plus sine squared theta is a Pythagorean identity that we saw the last time too. This equals 1. So we get just root sine squared theta cosine squared theta. D theta. And that's a perfect square, so we can just square root it. So it's going to be sine cubed theta times sine theta cosine theta. So we multiply the sines, get sine to the 4th, theta, cosine theta, d theta. And now the terrible part is over with. We can do this with a u sub. I'm going to take u equal to sine theta, because we're going to get a nice cancellation with the cosine theta. So 6 pi a, I'm going to drop the bounds because I'm lazy, u to the 4th, and this cosine theta divides with that cosine theta and they go away. So we just get du. So now we're ready to integrate. 6 pi a times 1/5 u to the 5th, doing power rule. Now I'm going to bring the 1/5 over here and unsub. 6 over 5 pi a. U is sine theta, sine to the 5th a. Or sine to the 5th theta, geez. Bring the bounds back. Do you have a question? Oh yeah, sure. What? Why? We can get to you right after this. Am I gonna get blocked by the problem soon? No, I'm good. 6 over 5 pi, plugging in our bounds now. Sine of pi over 2 is 1. 1 to the 5th is still 1. Sine of 0 is just 0. So we just get 6 over... Wait, that's not right. It should be a squared before I even look at the listen. I just randomly dropped that it was squared. I think I'm still slightly off though, right? Yeah, you're right, Penbox. I thought Zach put like an 8 over something though. Did I mess up a coefficient somewhere? I feel like I'm right. Critical, do you have the answer? Oh, 3 over 8 is the whole curve? We're doing surface right now. I don't know what, is 3 over 8 the volume? Either way, critical has the answer, right? Okay, the wrong part of Wikipedia. No worries. It is right. Ooh, hell yeah. So yeah, the factoring at the first part is messy, but if you can work through that, you're kind of home free after. So she got most of the pie in the marriage, so pie is approximately 0 in the divorce. Y8. No worries, critical. I assume you're gonna have more, but let's, since we've already answered quite a few from you, let's look at Y8s. What's your question, Y8? Can you compute dot? Oh gosh. So I was just trying to answer this question for Thunder last week because I didn't actually know the answer to it myself. And the conclusion that I came to is the dot product on its own doesn't actually mean that much. It generally behaves pointy times pointy rock. So it's helpful to know that they're, okay, Zach just talking about that too. But generally the dot product, because of that cosine theta, okay, let me actually write out the formula here. So Zach can give you a much better explanation of what it actually means, or like how to think about it than I can, but I'll give you my like basic understanding here. I'm sure most any of the other masterminds could give a better explanation than me. If you just have A dot B, the formula that I think you're talking about here is the magnitude of A times the magnitude of B times cosine theta. And this scalar in a vacuum means very little, is the answer. It's helpful to know how it behaves though. It does scale with certain things. So if you have like really big vectors, your dot product is going to be bigger compared to like vectors in the same direction but smaller. Like the red vectors would have a smaller dot product compared to the blue vectors. Vectors that point more closely in the same direction have a bigger dot product. So if we just pretend that these are the same, these blue vectors are the same length, this has a bigger dot product than that because they're closer together. And so but like if you just have general vectors like this, A and B, it really doesn't mean that much because it could be a lot of different things that's influencing the value that you get. Yeah, exactly that, Y8. And so, but the thing is, like, if you know, like, those two concepts where, like, the bigger magnitude gives a bigger dot product and the closer they are gives a bigger dot product as well, you can kind of do some fancier things with special cases where, like, if you take any vector A and dot it with any unit vector U, you can kind of get a measurement of how close A is to that unit vector, like how much it differs, which I think is what Dr. L was after with the whole projection thing. It's like if it's a unit vector, the magnitude of U is just 1, so it reduces the magnitude of A times cosine theta. So you're really just like taking the part of A that's in line with U. So it's the magnitude part of it. Then A cosine theta, yeah, exactly. So yeah, my general response is that the dot product in a vacuum, it doesn't, like, it means something, but it doesn't really mean that much. In the context of a specific problem though, it can mean a lot. Normalized dot products give an indication of angle. Okay, so Oh, true. So yeah, if you rearrange the formula to divide out the magnitudes, I think that's like you're just taking the unit vectors of each and seeing like how in line their unit vectors are. And that removes the issue I was talking about before with the blue vector and the red vector having different dot products if you make it all normalized. So yeah, if you're just like learning dot product for the first time, I wouldn't read too much into what it actually means. Just kind of know generally how it behaves, and that way when you encounter an application of a dot product, it'll be easier to understand why they're using it. Yeah, I hope that it's like helps you out a little bit. If you have anything else, let me know. In the meantime, if I see anything else from you, White, I'm going to bring up criticals. Next question. Hey, Ishan. What about cross product? No, we're talking about dot products on the board there. Yeah, no, it's all good. Critical, are you here for this next one? Okay, cool. Tunes back into dot products. Oh, well, 2 weeks ago, I was just moving on, but there's still gonna be some discussion in chat, it sounds like. What White was just asking how to interpret what the dot product actually means. And my very basic answer is that it doesn't mean all that much without context. Similar question in your test, they told us to find the volume by rolling around the x-axis or the y-axis. Oh, yeah, you were doing it around the y-axis. So give me us rotating about the y-axis. We're given the function in terms of y. So we could do like washers. This is hyperbola, isn't it? Half hyperbola. It's a circle, you're right. The signs, yeah, I was getting mixed up because it's like, oh, positive x and negative y, but they're on opposite sides of the equation. You're right, it's a circle. It's the upper half, or the right half of a circle. No? Yeah. All right. We're on the y-axis. I don't... 0 is less than y equals than a over 2. Is that right? Okay, so I think we could blindly plug into the formula for washers here without worrying too much about what the graph looks like. But no, I think we're fine. But I still want to draw a little picture of it though, because I feel like I might do something slightly wrong. Because like the 0 less than y is less than a over 2 is a little bit weird to me. It'll be a circle? Yeah. It's only half a circle though. Which doesn't actually, well, doesn't matter. I guess it doesn't actually matter for the actual volume, but. All right, so what we're saying here, critical, is we have x equals root a squared minus y squared. And what you can do is you can actually rearrange this to be in the equation for a circle. If you square each side to get x squared equals a squared minus y squared, and then add y squared to the other side. This is the equation for a circle of radius a centered at the origin. This part isn't actually all that important. I just like to have an understanding of what I'm revolving before I actually integrate it. For a simple case like this one where you don't have multiple curves, it's not all that important. Now, importantly, we weren't given this. We were given this. First line, x is always positive because the square root is always going to have a positive result. So we're only worrying about the right side here where x is positive. So it's actually going to be half a circle of radius a. Minus a. In terms of the length, I'm not writing the actual like points, but semicircle on the first and second quadrant. First and fourth quadrant, right? Yeah, rotating around the y-axis is going to make it a sphere. So if you rotate this around the y-axis, we're going to just end up with a sphere. And the volume of the sphere is 4/3 pi r cubed. So we can expect to see an answer like that. I guess with a, oh, no. We won't expect to see that. Because we're not doing the entire semicircle. We're doing 0 is less than or equal to y is less than or equal to a over 2. It's like a 9. So we're actually rotating like this part. It's almost like a sphere if you cut out just like a slice of it, I guess. It's area? Oh, it is area. Thank you, Fembox. I keep not reading the instructions. Dang it. Okay, let me look at the formula here. I was being so good at looking at the instructions for the other problems today. All right. Yeah, this is a surface, or this is a surface of revolution, not a volume of revolution. So if we're doing surface rotating about the y-axis, oh, this has the same like opposite thing. So we're going to do 2 pi x since we're rotating about the y-axis. 2 pi x times root 1 plus dx dy squared. Okay, we can do that. Yeah. It would benefit from a change of variables, but I don't think we get to do that. I'd love to do a double polar integral, but well, would it be double polar or would it be I don't know. Let's not worry about it though. Let's do it the way that we're probably supposed to do it. What's the formula again? I already forgot. 2 pi x. Okay. Can you derive the formulas once? Not without a lot of studying. At least some studying. I just have the formulas memorized, or not even memorized. I just never bothered really learning the derivations of them. So the formula we want is 0 to a over 2, 2 pi x root 1 plus dx dy squared dy. All right. So it doesn't work as dx dy, and we normally see as dy dx, but it's just, this is flipped because we have x in terms of y rather than y in terms of x. So it's the same exact procedure here, but we're just gonna, let's get dx dy, which means we're just treating y as our variable here. So taking the derivative of that, we start by doing the power rule for the square root, so we multiply by 1/2. And then we do 1/2 minus 1 for the exponent, so a squared minus y squared to the minus 1/2. And then chain rule, multiply or derive the inside, which is minus 2y. Ugh. Just you know how the formula's coming would help. I probably would, but I'm not gonna bother right now. All right. So let's simplify this derivative before we do too much. So 2 times 1/2 is 1. The negative sign, let's bring it out front. And a negative exponent is the same as being in the denominator. So let's make a fraction. Root a squared minus y squared. Then we have a y over there. Okay. And I think that's good enough to plug into here. X is root a squared minus y squared. 1 plus this thing squared is y squared over a squared minus y squared dy. Because the square root squared cancel itself, and y squared becomes, or y becomes y squared. Okay. Yeah, Fembox. I caught myself for one of them, and I was like, who cares? All right, so to deal with this, I think I want to bring these under the same square root, which we're allowed to do because we're multiplying. So let's do that. I'm going to bring the 2 pi out front as well. So if you have square root times the square root, you can make it one big square root. A squared minus y squared. 1 plus y squared over a squared minus y squared dy. And now we're going to nice cancellation a squared minus y squared times 1 over a squared minus y squared. Or, a squared minus y squared on the bottom. So a squared minus y squared times 1 is just itself. A squared minus y squared times y squared over a squared minus y squared is just plus y squared. Dy. 2 pi 0 to a over 2. Oh, that's convenient, isn't it? Minus y squared plus y squared is 0. Okay. Well, 0 to a over 2. Root a squared is just a. And a is even a constant, so we could bring it out front. Who cares? So yeah, we just get an empty integral basically, which is just y. 2 pi a y from 0 to a over 2. 2 pi a over 2 minus 0 when we plug things in. So we just get pi a squared, don't we? That's clean. That's just the radius of a circle. What the heck? Or the area of a circle. So, sorry. That's kind of a neat fact. The area of the circle is the same as the surface area of like one slice of a sphere. Goodbye, marker. Correct? Oh, awesome. SG1, great. Great. Oh, true. Penbox, yeah. I've been drinking nearly enough water this stream, jeez. Paint the sphere with 4 different colored stripes using the same amount of color of each paint. Yeah, I was just thinking, like, we've divided up the sphere into 4 equal surface areas, which is in a surprisingly clean way. Anything more critical? Doing this question in class 12? Oh, cool, SG1. I don't think I've done that exact one before. Sounds good. You can do surface area with polar coordinates. Assuming you don't have the answer? Okay. Yeah, so this would be a nice way of doing it instead, but I don't think you have these. Oh, maybe it's not that easy. Because you're doing like a horizontal slice rather than like a sector with an angle. Okay. Curve is rotated about the y-axis. All right. How far can you get with this one critical? Hey, Hardlucked. How's it going? Going okay? It's better than bad, I guess. I'm doing good. Just we had some good questions today. Critical. Do you know what's it called? The shell method? I can never find. Wait, is this surface again? Dang it! Never mind. Forget about shells. Why are these always surface? Sorry. So I mean, with surface area, we're really just plugging into the formula. Could you even like? I feel like I'm just kind of doing your homework for you here. Like, I don't think that's your intention, but like I'm just doing it. Like it's just gonna be the same procedure as last time. It's not a homework. That's fair, I guess, but like if I'm just doing them all, I feel like that's maybe I all right. If you're at least doing that self-study component too, then I feel better about it. If all I'm doing is just like showing you how to do problems and you don't do anything else, then I don't think I'm actually helping you, and I could be spending my time doing other things. But as long as you're like trying these for yourself, that's a really important piece of this. Like, that's like the most important piece here. So I can do these all day, but if you're not doing them, if you're not trying them for yourself, then it's not going to actually sink in. How do we do this around the y-axis? How do we get dx dy? So this one, there's an issue. They're asking us to rotate about the y-axis. And if you want to rotate around the y-axis, you need to isolate x and get a function in terms of y. And that's not possible when you have an x squared and ln x mashed together like this. I think Fembox is saying the right idea, which is we have to do some implicit differentiation. Or we can find dy by dx and flip it, right? Or that's a valid thing to do, right? You just find dy dx and then do 1 over that. I still be the same thing as dx dy, or like, you know, it should end in the same result. But what do we do for x? Yeah, we need it in terms of y. You're right. Ask you a different question? All right. Yeah, I mean, this one's a tough one. I don't know. I don't know how you set this one up. I want to do this one instead. Is the problem volume or surface area, or what are they asking for here? So same instructions as, oh, okay. Are the same instructions as this one here? Or on the y-axis, and we want area. I feel like this is the formula for that thing that we're just looking at before. Just out of curiosity, I want to put this in Desmos. Yeah, it is. Funny. So we're rotating around the y-axis. So we want to take this equation and isolate x to get something in terms of y. So 2/3 y to the 2/3. It's 1, 0 less than or equal to y less than or equal to 1. Okay. So yeah, let's isolate x, we said. X to the 2/3 equals 1 minus y to the 2/3. Then we'll raise each side to the power of 3/2. That's not going to be easy to integrate. Well, let's try plugging into the formula and seeing how it actually looks. Maybe it won't be that bad. Y goes from 0 to 1. 2 pi x. Oops. Oh my god, I wrote x again. 2 pi x, then x is that thing. Then root 1 plus me dx dy. Start with power rule of 3/2. The 3/2 comes out front. This becomes 1/2 times chain rule derivative of the inside minus 2/3 y to the minus 1/3. Okay. So let's rewrite this a little bit. 3/2 times the negative 2/3 is negative 1, so I'll just stick a negative sign out front. That's root 1 minus y to the 2/3 over y to the 1/3. So in the formula, it's dx dy squared. So if you square this, the negative goes away, the root goes away, so it's 1 minus y to the 2/3 over y to the 1/3 squared is y to the 2/3 dy. That's what we have to deal with. Let's make sure I did that vaguely correct. Yeah, okay, so make sure I didn't mess the formula up. What do we do with this? All right, well, we can definitely split this up and bring the constants out front. So when you have addition and subtraction in the numerator, you can split it up into two different fractions. So let's do that. So 1 over y to the 2/3 minus y to the 2/3 over y to the 2/3. I did that because of this cancellation here. Oh, I have to sneeze, but it's not coming. Ah! Terrible. I hate that feeling. It's 3 over 2. Okay. That's not the end of the line. Make sure that I'm not on mute still. Okay. So we have 1 minus, this is the y to the 2/3 cancel and we get just 1. So 1 minus 1 is 0. 1 over y to the 2/3 dy. And actually, I'm going to rewrite that. Really? Y to the 2/3 is the same as y to the negative 2/3. It'll make it a bit more clear how the square root interacts with that for the next step. So the square root is like an exponent of 1/2. An exponent to an exponent multiplies. So negative 2/3 times 1/2 is negative 1/3. Okay. Oh, there's a u sub here. Okay. So I'm going to take u equals to 1 minus y to the 2/3 because that's just, it's going to be a terrible integral if that u sub doesn't work. Well, it's already a terrible integral. It's going to be even worse if that u sub doesn't work. So I'm going to do that and hope that it does. And I think it actually does. Because that means du is minus 2/3 y to the minus 1/3. And I think this y to the minus 1/3 is going to cancel with that y to the minus 1/3. It does, yes. Because just to make it even more clear, I'll rewrite this. I'm going to multiply each side by negative 3 over 2. So negative 3 over 2 du equals y to the minus 1/3 dy. And we have a y to the minus 1/3 dy right there. Y to the minus 1/3 dy, so let's put a negative 3 over 2 du there. And negative 3 over 2 is a constant that can go out front as well. Negative 3 over 2 times 2 pi is negative 3 pi. 0 to 1. Oh, sorry. Drop the balance for now. Because we're doing a u sub. U to the 3 over 2. Good. That's something we know how to integrate. Oops. It'll be 2/5 u to the 5 over 2. Now let's unsub. So we said u was 1 minus y to the 2/3. To the 5 over 2, divided from 0 to 1, bringing the bounds back. Oh, geez. Hey, Skirtle. What is that emote? Let me look. Oh, is that new? Either way, it looks adorable. Minus 3 pi. 2/5. Okay, so when we plug in 1 to the 2/3 is still just 1. 1 minus 1 is 0. So that actually goes to 0, thankfully. So now when we plug in 0 to the 2/3 is still 0. 1 minus 0 is 1. Just to get 1. And 1 to the 5 over 2 is still 1. Okay, good. So we get negative 3 pi times negative 2 over 5 becomes 6 over 5 pi. Hopefully that's the right answer. You made it last night along... Oh, what? Those look so good. I love those, wow. And the one for Jake too. Love it. You don't have the answer? Let's plug it into Wolfram then. I definitely wouldn't trust my ability to not make a mistake with an integral. Yeah, $10. I think it's not the same exact setup. I don't even remember now, to be honest. It might be. We want to make sure that I followed the integration through correctly. We won't be able to check if I set it up right, I guess. Oops. What am I doing? No, what? Why would you do that, Wolfram? 2/3. Oh, Wolfram's gonna freak out if I don't. Star there. And Divide Nick, hey, welcome in. You got your results for the A-level city of the Oracle exam and it went so well. 94 out of 100? Dude, great job on that, Nick. It's awesome to hear. Use dot product and magnitudes to calculate angles between vectors. Yeah, exactly. It's a nice application of a dot product. Okay, let's see what Wolfram does with that. 6/5 pi, like, it looks right. Right? Wolfram doesn't know how to do it? And does it even do it numerically? Wait, what? Oh, dx. Never mind. Told it to do the wrong thing. Didn't do much. Oh, really? Oh, yeah. I was wondering, like, I appreciate it, but I was wondering why, like, oh, you know, I don't remember, like, helping you. Oh, I did something wrong. But hey, thank you so much for the kind words. Yeah, apparently it's 6 pi over 7. I went wrong somewhere. Unless... Oh, no. This is 3 over 2. Not 5 over 2. 6 pi over 5? There we go. That's right. Hell yeah. No worries. I haven't seen that Dunce Hat Twitch emote before. That's a nice one. I gotta start using that. For now, that's all. All right, sounds good for critical. Thank you for the questions. Give me 1 second. Okay. Sorry, I like a bunch of pings on Discord right now, and I can't mentally deal with that. I have to see like what these are. Okay, yeah, I didn't need to check that yet. All right, anyway. Air Surface Revolution. 12 pi over 5. And right, we did only do half because y was from 0 to 1. Okay, cool. Thanks for looking that up, $10. So from creepy face to monkey face. Oh, really? What is it for me then? Yeah, the creepy face I kind of hate. I need to look up how you... Wait, what? Oh, that doesn't even do anything for me. Hey, Han. Yeah, we're just doing some surfaces of revolution. Yeah, I don't like the default like face that comes with like my thing. It just looks kind of weird. Yeah, we had to do the surface area revolution for this thing around the y-axis, so it was a. Actually, the integral wasn't as bad as it could have been, but it could have been bad. Oh, really, Fembox? So was it possible to... Or how do you deal with the x in the formula? Oh wait, you can just translate the y-coordinates to x-coordinates, can you? Or like, can you convert it to be in terms of x somehow? Maybe not. You put it all in terms of x. Doesn't that get you a revolution around the x-axis though? Let me look at the formula again. Seem to be increasing. Wait, it wasn't parametric. No, not that. Here, there. You're using this formula. Well, since we have some time, we may as well take a look at what it looks like. Y equals 1/4 x. Oh, what the heck? Ooh. It's like a parabola with its pinky up. That's how I see it, at least. And then our interval is x is between 1 and 2. Yeah, that's fair. Say that it's increasing, at least. I don't know how the surface... I still don't know how you deal with the surface being around the y-axis, but... Oh, man. Either way, I think I might take a quick bathroom break. And maybe we'll do some physics. I don't know. We'll see. We can see how we feel. Put the formulas on Paul's notes. Really? Oh. You're right. Yeah. Okay. I was making the connection in my head that the first formula here goes with the first formula there. But it doesn't have to be like that. You're right. You can like mix and match. Okay. But yeah, I'm gonna put in my BRB screen. I'll be back in just like a minute or two. Yeah. Okay, back. So yeah, since I don't think there's any questions from chat. Uh, we'll probably just do some physics. That sounds fun. Get some water though. Okay. take a look at maybe number 8. It looks complicated because I saw the word Taylor series. That's the entire reason why I'm even looking at it right now. Worked out number 6. Oh yeah, I remember seeing. I'm thinking that I saw Stuki do the calculation for part A. I want to do the calculation for part B. And I remember having this whole discussion on part D. And halfway through, I just looked at the answer and I was like, oh, okay. I won't spoil it unless you want to. Unless you already, like, know the answer to, though. Triangles. Yeah, I think it'd be a good exercise to go through the pain of that one, but that's probably an off-stream thing. So this morning worked it out. Oh yeah, I mean, I looked at the answer key, and even then it didn't use that much of a calculation. I was kind of like, oh, you know, if you do this thing, that's probably the path that they're talking about. Yeah. We were. I think we were just making it too hard. Or like we're making it harder than we had to. Parametric radius R is uniform positive charge density lambda. Particle with positive charge Q and mass M is initially located at the center of the ring and is then given a tiny kick. It is. I smell a differential equation. No, it's probably not. It is constrained to move in the plane of the ring. Oh. Oh. Yeah, this one looks hard. It is a 3-star. What is a 4-star problem? That's, oh my god, okay. I should switch up the playlist. 1 second. That was a weird noise that I just made. Let's do, I guess, lo-fi. So, a ring with radius r has uniform positive charge density lambda. A particle with positive charge q and mass m is initially located at the center of the ring and is then given a tiny kick. So these are all positive charges involved. If it is, and so this kick is towards one part of the ring. It's not up or down, like perpendicular to the ring. And it undergoes simple harmonic motion for small oscillations and find the frequency. Find the potential energy of the particle when it is at a small radius r by integrating over the ring. Then take the negative derivative. Need the law of cosines and the Taylor series. Okay. Please take it one step at a time here. The potential energy of the particle at a small radius r. I don't know if I can do this, but I want to try. They said the word integral, and I'm doing this for the integrals. Like, you know, I'm hooked. I bet you could do a differential equation for this too. I guess it's probably not necessary, but... Let's crush this problem. Well, actually fine. So we need the potential energy of this thing. U equals epsilon naught over 2 e squared dv. Is that the formula that we want? I'm a little confused because isn't, like, why isn't the field inside of this 0? The field inside a ring. The field inside a sphere is 0. Why isn't the field inside a ring also 0? Because, like, if you make your Gauss's law solid, I guess Fedbox, it's just, that weirds me out. A sphere is closed, but a ring isn't? Man, when we were breaking that cone up into rings, though, or even when they did the hemisphere problem with rings, they were making the claim that the horizontal, or like, you know, we were saying that the field inside of that ring is 0. I could just go with it, but like, I feel like this is... I don't... It'll certainly have a field at, like, if you go perpendicular to the ring, there's definitely a field there, but like inside the ring... I don't know. So the formula is just the magnitude of E for potential energy. So we get to ignore the vector r because it's a unit vector. It's just a circle with circumference 2 pi big R times lambda. So yeah, Fenbox, I feel like I've been hearing contradicting things on that because like I remember like my intuition for this situation is probably like the worst out of all my intuition for E&M because like I remember asking Milk and Horns this specifically, and Milk said, or like I remember, sorry, for the situation of a spherical shell, if you put a charged particle inside of a spherical shell, is it going to move towards the center or just stay put? And Milk said what I thought was the same answer that the textbook would say, which is it'll just stay put because the forces cancel itself out. Like all the forces just cancel. But this seems to imply the opposite, and I don't know how to reconcile it. Inside a spherical shell, you agree that it'll just stay put. If for any point inside the spherical shell, not necessarily just the center. I'm not sure why a ring, if we're constrained to the plane of that ring, is any different, I guess. You said correct to that not necessarily being in the center part, and it still holds. Okay. Because the argument that I would make for there being a field inside the ring, I feel like I'd make the same argument for why there could be a field inside. Well, maybe that extra dimension does help. Does it? I have no clue. And then bend and escape in the third dimension. Oh, okay. I guess I can see that. What circumference of a circle is 2 pi big R times lambda over R squared. 4 pi epsilon naught. Wait. Oh yeah. So we do get a cancellation. Sorry. No, that is little r right there is fine. Like that, I want to say. Field lines that start inwards from the ring towards the center, but then bend either into the whiteboard or away from it. Okay, and we're arbitrarily saying that this point can only move in in the plane, or it's perfectly level, which I guess is how we can justify that somehow. R is going to go from 0. Oh, I'm using R in too many different ways. Let's call this small kick distance R sub 0, I guess. So I think that's what they want. How did I come up with that formula for E? The total charge of the ring is the circumference of the circle times the density, because lambda is linear density. And the rest is just should be more complicated than r squared. Is that the issue? I mean, I guess it's technically yeah, maybe the r is, I'm being a little too simple with the r. Do we take like a chord of the circle? And break it up into two? Like we would integrate this part different when we integrate that part? Well, how do you draw that chord, I guess? I just have a unit circle in an xy plane, what is the distance from the circle to any arbitrary point? Like there. Is that the question that we have? And how do you do, like, what part of the circle are you measuring the distance to? Maybe we have to answer that question before we can even proceed with an integral, right? Yeah. So I think there is some chord that we can draw such that all the charge from like this sector of the circle pushes the charge towards the center, and all the charge from this sector of the circle pushes the charge away. I assume that we have to do something like that. I don't know how we do that arbitrarily. So if we completed the radius, I guess we would be interested in whatever the perpendicular is. That's probably going to be our cutoff point. Yeah, okay. We came to the same idea there, Fembots. I mean, we could make it easier on ourselves. Like, there's no reason we can't... instead of doing a diagonal, let's just do it like perfectly horizontal, I guess. So let's bring the xy coordinates back. let's consider just a perfectly horizontal kick, such that our chord goes straight up and down. That displacement is r sub 0. So when x equals r sub 0, y squared is r squared minus r sub 0 squared. Oops. I don't know if this helped us yet, but yeah, okay. You mean this similar constraint? So what am I trying to say here? Maybe this is better expressed in polar. It almost is certainly better expressed in polar, right? We need to work out the angle from the origin to the top and bottom. I mean, we could look only at the quadrant 1 part and multiply it by 2 for whatever field we get. I guess the magnitude of that, anyway. Maybe it's not better done in polar. Polar is going to... maybe if r is a function of theta, you can make polar work. Just a vertical line in polar isn't the cleanest thing. Like, I'm thinking, if we can work out, like, the angle that goes to the top and bottom parts, our polar like our radius needs to go from some minimum distance out to the entire distance. So like as far out as r, might be overthinking it. I'm going to use the U integral in line 3. Remember guys, r in terms of the angle. Yeah, I guess it would be R0, comma 0 with the notation that I arbitrarily made up. The integral I have on line 3. I don't know. Yeah, I guess my U integral isn't quite right because it's not this simple with the R that I have. Parameterize R in terms of the angle from the charge after it's displaced. Wasn't that going to be minus pi over 2 to pi over 2? If we're doing it after it's displaced? It seems like the hard... Yeah, I did forget to square it as well. Yeah, I haven't defined my little r well enough, for sure. You're gonna tea with the tea bag left in? Oh no. It tastes so bad when you do that. I don't get how you and Stooky can both like do that. Well, I mean, I guess I can appreciate the whole like laziness excuse, but I don't know. I just I let my tea steep in the kitchen, and then I just put the tea bag in the trash can after it steeps. Just in general, how could we find the circumference of like the outer or the inner part of the circle? Like that would be a help. Like I guess we have to set up a right triangle here. What's what though? We only know one side, we don't know anything else about this. That's an isosceles triangle if we consider the upper half. An isosceles triangle with height R0. Is that enough information to work out anything about this? These are big R. That's maybe enough information. Is that what we need law of cosines for? Huh. No, there should be an easier way. This... So the angle up here is pi minus 2 arcsine r0 over r. I don't know if that's helpful. I mean, that would mean this green circumference it's 2 pi big R times whatever this angle is in radians, right? We don't have to think about it much harder than that. Or we have to divide it by 2 pi. I think we have to divide by 2 pi. No? Wait, yeah. Because this is like a scaling factor for the entire thing. I actually didn't end up even using the law of cosines there. I don't know if that's, I don't know. U equals question mark integral. Let's write down what you're saying. Question mark and all. Question mark integral KQ R lambda d theta. KQ R lambda d theta over R squared from 0 to 2 pi. And R is a function of theta. What is theta here? Theta is just the angle between the x-axis, or like, theta is just like the normal theta for like a unit circle, I guess, if we're constrained to the x-axis. You're saying that u equals that. Are you saying that the field is the thing inside the integral? Because shouldn't we have to square it? Is charge a red herring here? Milk, I was getting confused on the whole, like, is there even a field inside the ring thing? I assume this question wouldn't be asked if there was no field inside a ring, but I'm just kind of going with it. what's written on the... I have a hard time understanding what's written on the board exactly is. You hadn't read it properly? Okay. I have a hard time understanding where the center was coming from. Okay, let me at least put my mind at rest about one piece of what I wrote in green. Oh yeah, arc length. S equals R times theta. Okay. So yeah, if my thing, you would divide by 2 pi. Yeah, I think we have something like the formula for force. So I don't know. I have no clue if what I'm writing here is going to be helpful, but really, ugh. I'm just going to keep it going. The 2 pi's cancel. And so you could get the charge of just that part by throwing a lambda in there. Now, why is this helpful? I haven't worked that part out yet. It looks cool though. This is hopefully helpful because this green part of the circle is what's exerting a force to the left. If we put a cosine theta on it, you want to take that magnitude of E squared thing, like this thing? I mean, I intentionally erased the R squareds from the denominator because I didn't know how to define R squared. Dang it. I hate when we need actual, like, geometry. Yeah. And I mean, actually, if we know like that green arc length, you could do 2 pi r minus it for the rest of it. I feel like I'm not doing this right still. I don't know. You gotta get dinner and or paper. I had dinner and you have paper and you're still stumped. I mean, I'm gonna need dinner at some point here, but I want to keep thinking this for a bit longer though. Like, I almost wonder if this approach isn't even right. Or if it needs, I mean, or maybe it is right, but it needs something else also. It's like, I'm wondering if maybe we could completely just consider something, honestly, I think my first circle is my best circle. They're getting gradually worse the more that I draw them. Should we just be thinking about what's the contribution from this tiny portion here, for example? The offset makes it so much harder to do anything with this, though. Oh, wait. There. Okay. Maybe I might be cooking. We can make a triangle from here to here, r sub 0. Add in this little side down here, which is big R, and solve for that final length? Maybe? We don't know anything about the angles though, do we? It's like if we wanted to get that third side, oh, we don't know any of the angles. Ah! Well, the angle could be the variable. Like if that's theta. Well, I guess it'd be d theta. No, it'd be the angle from there, like out to r is theta. No. No. The angle from the x-axis down to big R radius is theta. If we're going to make this claim. And then law of cosines to get that third side would be r squared plus r0 squared. Oh, I keep writing a 0. Minus 2 r0 cosine theta? And that will be the length of this lower part. Hey, Zyrak. What do you get from these questions? Pain. But some fun. That's basically trying to use a lot of cosines on. Oh, okay. Oh wait, where do you get these questions? I'm sorry. Yeah, yeah. 10 bucks of the book there. It's for a reading group that I've been hosting. These problems are really fun, but this one is an especially challenging one. Normally they aren't quite this hard. They're ones that we've been doing. So what would we want to integrate here? Or like, what would we do with this? Like, we'd be saying that do we want the S? So theta is measured from the origin, but distance is measured from this offset. That's the part of this that's really tricky. Calculating the field instead of the potential. Potential is easier, but sometimes it is. I would take either. I don't know how to... I mean, I thought they rest on kind of the same thing. WECE. Oh, fair. Yeah, I mean, this has just been something that we've been doing for fun, so it's not like a high pressure thing or anything. I managed to pass my calculus-based electricity and magnetism class during college. We never had to do a problem that's quite this hard from scratch, but I feel like I didn't really understand anything and I didn't find it that fun at the time. But I think with more math knowledge now, it's been a lot more fun. Technically that's square rooted, but we can prime, I guess. I don't know, it's terrible notation. Potential is a scalar function, while field is a vector function. Well, I guess the distance, I guess, is what we're kind of all struggling with. I think, though, Milk. Like, that's what I'm working on down with my circle stuff down here. Maybe this is terrible. Should I say that's R sub 1? That dotted line? I feel like R sub 0 prime is even worse than R sub 1. Hey, Bob. Join every 2 weeks and something wild's going on? Yeah, I'm doing a physics reading group now on electricity and magnetism. We're trying an especially hard problem that's giving us all a lot of trouble. It seems fun though if we can like figure it out. It's just trying to calculate like if you have a point right next to the center in a circle, how do you get the distance from that point out to the edge of the circle? I guess is what we're immediately working on. How's it going though, Bob? Chilling, that's good to hear. Ugh. I feel like I'm starting to get kind of the right idea here, but like... I mean, is this enough? Can I just... If I integrate a thing I have from 0 to 2 pi, could we get the field, or even just go straight to the potential? So can we work out the magnitude? No, I'm probably not gonna have TTS on my stream. I hate the TTS voices. I just like the generic like robot ones. Either way, I'll take the 1 bit though, thank you. U308 2022, thanks for the follow. Actually, yeah, it is a volume integral. I think we would convert it into a area or single. Like we would like reduce it down, I guess. But yeah, the V is definitely volume. Okay, I remember this portion of the text was super confusing too. Not important to the discussion at hand though. Do I actually have... Oh, yeah. I mean... I don't know. I have my viewer count turned off, so I don't keep that big of an eye on it during the stream. But when I go back and like look at my average viewers like throughout the stream, it usually just like ramps up over the first like 2 hours, and then it kind of maintains somewhere around like 18-ish. Volume integral check, density itself per volume. Yeah, I guess the density part maybe takes care of that, like Dr. L says. Back in the day when you streamed, you also had viewer count off? Yeah. I assume you're like a Trackmania days? Or do you mean like the math streams too? That's the word. Yeah, so we'd have like dv equals 2 pi r, no? Maybe just 2 pi dr. Or not, I don't know. It'll work itself out, but yeah. Just don't ask me specifically how, I guess. How do you contend with E dot E when the same field is pointing towards itself at some places? Well, I guess when you only consider it from one direction. Thanks for the work. Well, that's what I'm trying to figure out. Like, that's what all my weird triangle stuff is for. Well, actually, I mean, yeah, we definitely do not know the field for an arbitrary point inside that circle. And that's what I'm trying to figure. Oh my gosh. You learn calculus, you got A's in calc, didn't really understand until E&M. This is really helping me understand the whole differential notation. It's absolutely done that for me so far. Because I hardly ever use it in my calculus class, but like thinking of things as like a small change in the potential energy is equal to like the field times a small change in R, or you know, with whatever like this is. Thinking about like intuitive explanation. I think this law of cosines thing is helpful in some way that I set up. Let me just make sure I got the sign right. That it's, yeah, it is a minus there. Okay. If I took that, because we're treating big R and R sub 0 as constants, if I took that and blindly integrated it from 0 to 2 pi in terms of theta, Well, we don't have to, okay. Let's go back to the board. Carnitas? Oh my god, Dr. L, that sounds so good. Enjoy. Who's that? Oh, Gold! Welcome in, everyone. Oh gosh, okay, let me, thanks so much for the raid. Hope your stream was good, Gold. Yeah, Lightning, Aneem, hey, Helldog, hey, Misty C Rift, hey. So yeah, for anyone who's new here, I do these math help streams and some game streams. Right now, there's no math help questions in queue, and so I've been doing this little physics reading group. And just in the downtime, I thought I'd pull a problem from that textbook and try and work it out. This one's a very difficult one, though, so... Oh, yeah, I mean, sometimes the time just flows by. It hasn't even felt that long. It's been a fun day. So yeah, we're just on chapter 1 of this book. It's been really fun. I really enjoyed the calculus that goes into it. This particular problem is not easy though. Thought I'm with the E&M. Oh, really? Yeah, or I mean, I should come in your stream and ask some questions. We're using, what are we on, page 41? Okay, just so I don't lose my track. Yeah, this is the book that we've been using. It's cool. It's not an easy book though. It expects you to like be really good with the calculus, it seems. Yeah. Not as hard as Jackson? Oh, I haven't heard of Jackson. I'm kind of glad that I didn't if it's harder though. Jackson's infamous? Oh, really? Just the question in this book, he's still... Oh wait, that someone been solved in general? Oh my god. That's kind of crazy. I hope they're not presented as like an exercise for the reader like these are. It'd be kind of funny. See if someone actually solves it. We need to do the line integral over the ring. Sure, Milk, but like with the thing that I made with law of cosines or some other thing. The book is notorious for the difficulty of its problems and its tendency to treat non-obvious conclusions as self-evident. 2006 survey by the American Physical Society. Oh, that's a weird name. Physical Society? Revealed that 76 out of 80 U.S. physics departments surveyed require all first-year graduate students to complete a course using the 3rd edition. Oh my god. Man, just a plain cover as well. I guess in the 2nd edition, maybe the 3rd edition. Has something nicer. Magnetohydrodynamics? Magneto? I don't know how you pronounce that. That sounds so complicated. I guess I'm gonna say advanced topics. Basically all plasma physics? Okay. Wow. Uses the 3rd switches to SI units, but only for the first 10 chapters. he had betrayed an agreement he had with Edward Purcell that they would support each other in the use of Gaussian units. Dude, the Gaussian versus SI units, I guess that beef runs deep. The Purcell book, every time they give a result in SI units so far, they've also given the equivalent one in Gaussian. Balanis, I haven't heard of that one. I should actually look at the integral that you wrote, Milk. V equals k times integral over ring of lambda dl divided by r, the absolute value of r minus r prime. R is a differential piece of arc. R prime is the position of our particle. R and R prime are vectors. Okay, so the magnitude of that vector. Where am I? I'm here. So R is the position of a differential piece of arc. R prime is the position of our particle. And dl is the differential piece of arc in question. Okay, I need to unpack this. I keep using the wrong side of this marker. Okay, so if that's R, and this is our dl, and that's R prime. So well, these are vectors, I guess. Vector. Vector. You're interested in the result of R minus R prime and the magnitude of that. That's what you're saying. Really? R prime, oh, well, that sucks. Okay, so R prime is that. Vector. R is equal to R times R hat. R prime is the xy of our particle. Okay, and R hat is just the unit vector. Okay. Convert that. Convert x hat and y hat to polar. Okay, wait. Vector R. I assume the magnitude is big R times r hat, and r hat is that 1 over r squared times something, the actual vector? Well, I guess maybe I shouldn't think too hard. If it's a circle, wait, the magnitude of the vector is just r. R cosine theta, r sine theta? That's definitely a unit vector. Okay, we got to the same spot there, Fembox. I guess is equal to, if we want it in polar, just r prime comma 0. X hat is cosine theta r hat. It is? I don't know what that even means. R X hat. Cosine theta r hat. Okay, so the x hat is the unit vector pointing in the... No, I don't know what this means. Isn't y fixed to be 0 though? Yeah, so okay, I'm figuring that we have r prime equals to x hat plus y hat, and that I've lost my train of thought. Where do those come from? The x hat and y hat formulas? Is that just like a general conversion formula? Okay. So the R prime vector is x hat and y hat. I guess these are unit vectors, so should we have an actual magnitude here? Or not magnitude of x hat? Seems like the magnitude of x hat is a variable, and the magnitude of y hat is always 0, isn't it? That's why I'm kind of confused. It's like it's not just x hat plus y hat. They check out? Okay. Yeah, Zach. It's been a fun day. And yes, it's just x hat. But we still need a magnitude, and that's going to be our variable? Like, are we going to call that r prime, I guess? Like, that's... I guess if we're saying that, then I can go with this then. Cosine theta r hat. Now, I guess where I'm confused is like, is this r hat the same as that r hat? Because I thought this r was particular to the radius of the circle, which I guess... I don't know. Minus sine theta theta hat. Well, and then since we're only constrained to the x-axis, this theta is always 0. So it's just still... But it's not like that same r. Like, I don't know, is this a different r? I think it has to be. Well, yeah, so I guess I'm calling the distance r prime 2, but maybe that's bad form. Hey, Tertar. That's what we're trying to do, but the distance calculation from the point to the ring is pretty difficult. Um, it's like my headphones are imbalanced. So I feel like I kind of cut to the chase and I figured out what this r prime vector would be. I'm a little confused at like the process that you're using to get there, but it is just like theta's always 0. It's just It's one-dimensional movement, I guess, so it's nothing that crazy. Well, it's restricted to the x-axis. So theta is always 0, is it not? I feel like it's a different theta that's here. Because the particles, we're making the claim that it's only, or I assume we're going to make the claim that this charge is only going to move back and forth along the x-axis. Do you integrate x squared plus y squared in the surface integral? Maybe, but it's not quite that simple. I honestly, I don't know what we have to do. I've been stuck in this problem for a while. Territar. I'm confused by this definition of r prime, the r prime vector, I guess, because it's just only going to be along the x-axis. It'll sometimes be to the left or to the right, and it'll change the magnitude, but I don't see why it'd be anything except for something like what I wrote. R prime equals x prime times x hat. Okay. Okay, so instead it's a t instead of a theta. I still don't get why, though. There's never an angle. That it's like the angle's always the same. Well, yeah, so like, I know we're going to integrate over the entire ring and that theta is going to change. But we're just, like, all we're doing for this section is expressing the vector r prime in polar, right? But that vector, it always points parallel to the x-axis. So I am confused why there's an angle in the first place. Like, we are going to have to integrate over an angle, and like it'll make an angle with the r vector. But it itself doesn't have an angle. Or, you know, its angle is always 0, I guess is a better way of saying that. Yeah, I mean, I think it seems like there's probably some convenient thing that could be had if we can work out the vectors here. This determines the direction of the r hat and the theta hat vectors. Well, yeah, I guess what I was gonna like. I'm sorry. This vector construction, it just doesn't make sense to me right now. I'm also terrible with vectors, but I can be on board with the idea that that length, if you want to get it geometrically or with vectors, is given by the, or you can get it geometrically with the law of cosines. Maybe I can understand why you need theta to not be 0 if you're changing the, like, you know, to determine whether you're going left or right. Oh, that could be it. And that would depend on theta, unlike the big theta. I guess that's... But we could just accept that, what do we want to call that distance? I don't know. What I want to do is just take that and just do law of cosines. Like that. And we integrate that 0 to 2 pi. Or R0. Delta R, or do we want to integrate this? Yeah, I mean, couldn't we plug it into the formula for U up there? That's what I've been like wanting to do, but I also want to understand the vector like interpretation, I guess. Should cancel. Like, is that our answer for the potential energy component of the problem? I mean, oh, like, is it the distance part or is it another part? Because the thing on top is just the total charge. It's length times charge per length. The circumference is 2 pi r. You can't just, I think you have to integrate. You can't just take the entire, well, the entire charge of the ring is constant. Like the charge inside the ring isn't changing. I feel like the textbook at least was doing a shortcut like that, like 90% of the time. Like you could justify it with integration too, but I think it wasn't any more complicated than basically doing charge per length times total length, or charge per area times total area for the plane, or whatever you want. As the little dl varies, our theta varies. L is equal to RD theta, that's what we would say. Or DL is equal to RD theta, because that's arc length. I mean, that's where the d theta came from. I just added that on arbitrarily. Okay. A difference in the electric field is equal to lambda times the arc length RD theta over 4 pi epsilon naught r squared. I'm going to go back to r sub 0 because I don't like writing r prime squared. It's too many things up top. How about that, Fembox? Move Q from the broken symmetry. I need to put a cosine theta on it. But yeah, you're right. Like, we have to add them vectorially. It is a vector, yeah, you're right. Okay, that's the exact same thing that I haphazardly came up with. I mean, yeah, we do only need the magnitude of it. We do have like an opposing field though, so like the net force on this. We can take gradient V and get E. Oh, interesting. Okay. Yeah, let's this is just like a part of the problem too. This isn't even like the only component here. Wait, are we integrating for the total field? Or can we jump straight to... I guess we're integrating, we're missing a square root. Are we? Like, this is equal to the square of the distance already, so we shouldn't have to square root it. Where else would a square root possibly be? We don't want the square? Well, for the field, we do. I know that potential energy is just inverse distance, not inverse square. But like we should end up with that. Like we start with inverse square, but by the time we integrate, we get just r. But we haven't integrated yet. I mean, like, maybe I shouldn't jump the gun and go straight to, like, should we start with the magnitude of E? And then just this thing not squared or anything? I don't actually know how you integrate that. It's not like a virus stress substitution? That seems kind of terrible. Yeah, I might need to call it for this one. I don't know. I just don't get it for now. Yeah, I'm wondering. So no, I've been wondering that too. Where I feel like we haven't dealt with one part of the ring opposing the other part of the ring. And I feel like we need to multiply by cosine theta to take only the component parallel to the displacement r sub 0. I just don't know how you deal with that, so I was just like setting up the integral to see what it looks like. 2 weeks of carnitas made? Doing it again tomorrow? Dude, that sounds amazing. Ugh. I want 2 weeks worth of carnitas so I can eat them all in one night. Four pork butts for like 55 bucks? Oh my god, that sounds amazing. I know, I'm gonna have to come back to the problem, think about it more later. I think I need to call it though, because I actually need some food for myself. All this carnitas talks make me hungry also. So yeah, I guess I see Zach is on and doing math, so we'll read out to Zach. Honorable mention to Penn Center, who's playing Zelda. And yeah. Oh, really? $10? Yeah, I mean, I want to figure this one out. I don't want to look at this solution, but it's not easy. 3 minutes of the talk. Oh, I hard agree with that, Dr. L. Like, I appreciate a nice sandwich, but tacos are just on another level. Goodbye, YouTube.